Hey team, today we're going to discuss cloud design patterns. So cloud design patterns are useful for building reliable, scalable, and secure applications in the cloud. Today we're going to be concentrating primarily on reference architecture to do with Microsoft Azure. However, the thought processes around these design patterns are really cloud agnostic. So they can be used within private clouds and public clouds as other public cloud vendors as well. So who am I? My name is Luke Murray. I'm a senior consultant from Hamilton, New Zealand. I'm Microsoft Azure MVP, and you can find me on the social media links below. Feel free to reach out if you have any questions, or anything like that. Now let's start by discussing some of the importance of design patterns. The first is reusability. So design patterns promote reusability by providing proven solution to common problems, allowing components and subsystems to be used in other applications and scenario, which increases the interoperability between services. The next is maintainability. So design patterns help simplify administration and development, making it easier to maintain and update applications because they're consistent. So going into consistency, design patterns ensure consistency and coherence in component design and development, which is crucial for the overall quality of the application or the services that you're developing. So let's take a look at some of the efficiency aspects. So by following established patterns, developers can avoid repetitive work and focus on implementing specific requirements, thus saving development time. Scalability. So design patterns can help by building scalable systems by providing guidelines for efficient resource allocation and management. They also help to optimize the use of system resources, leading to improved performance of your application. Design patterns also promote modularity. By making the patterns modular, and you can create your code modular and structured, making it easy to understand, modify, and maintain. So how do design patterns really translate to modern cloud architecture? Let's take a cloud platform ecosystem like Azure, with services offering a plethora of functionality to be put together like large Lego bricks. So the first is scalability. So cloud design patterns address scalability by providing solutions for horizontal and vertical scaling, ensuring that applications can handle increased loads of efficiency. This promotes sustainability by enabling dynamic resource allocation, reducing energy consumption during low demand periods. The next is resilience. Patterns like circuit breaker and bulkhead help in building resilient applications that can withstand failures and continue to function. Sustainable operations are achieved by minimizing downtime and resource wastage, thus ensuring efficient use of your resources. So security. Security patterns such as the API gateway and secure token ensure that your applications are protected against malicious actors, maintaining confidentiality, integrity, and availability. Secure systems also support sustainability by preventing security breaches that could lead to resource wastages. So when we look at operational excellence, patterns like Ambassador and anti-corruption layer enhance your operational excellence by simplifying the management and monitoring of cloud applications. Efficient management practices contribute to sustainability by optimizing resource usage and reducing unnecessary overhead. Performance efficiency. So patterns such as cache aside and compute resource consolidation optimize performance by efficiently managing resources and reducing latency. This leads to sustainability by lowering the overall resource footprint and energy consumption through effective resource management. So data management patterns address challenges related to data consistency, synchronization, and management across different locations, crucial for cloud applications. Sustainable data practices ensures that data is stored and processed efficiently, minimizing energy use and reducing environmental impact. So let's dive into some key acronyms commonly used in cloud architecture. First, we have service. In cloud pattern design, a service refers to a distinct function or a set of functions provided by a cloud application. These services are designed to be reusable and are typically consumed by multiple clients or consumers. For instance, in a microservices architecture, each microservice is a service that performs a specific business function, such as user authentication, payment processing, or data storage. Next is the term consumer. A consumer can be an application, a service, or even a user that utilizes the services provided by another system. The consumer sends requests and receives responses from the service. For example, a web application that calls an authentication service to verify user credentials is a consumer of that authentication service. Lastly, we have tenant. In a multi-tenant architecture, a tenant refers to a group of users who share common access to a software instance, but with specific privileges. Each tenant data remains isolated from other tenants. In SaaS applications, each customer or organization is considered a tenant, ensuring that their data and configuration are kept separate within the shared application environment. So let's start to look into the categories of patterns. So cloud design patterns are grouped into several categories or archetypes that help us solve a specific problem. The categories can include data management, security, reliability, messaging, and design and implementation. So let's take a look at each category in more detail. So data management patterns can help us manage data in the cloud. Caching helps us to reduce the number of database hits and improve application performance. Sharding helps us to partition our data across multiple database instances to improve scalability. Federation helps us to distribute data across multiple databases for better availability and fault tolerance. Security patterns help us secure our applications in the cloud. Perimeter network helps to isolate our application from the internet. Identity management helps us to manage user identities and access to resources. Secure communication can help us protect our data in transit. Reliability patterns help us to build highly available and fault-tolerant applications in the cloud. Retry helps us recover from transient failures. Circuit breaker helps us prevent cascading failure. Bulkhead helps limit the damage caused by a failure. Messaging patterns can help us to build scalable and decoupled applications in the cloud. Asynchronous messaging helps us to send messages between components in a non-blocking way. Event sourcing helps us to capture all changes in an application state. Competing consumers helps us to process messages in parallel. Design and implementation patterns can help us to build cloud-native applications that are scalable and resilient. Valet key helps to delegate access to resources. The ambassador pattern can help us to expose services to external clients. A very common one, gateway, can help us to provide single entry point into our application. So the cloud has changed the way we design our applications. Let's look at some of the design patterns that we can use in the cloud. These patterns can help us solve common problems in cloud architecture and make our applications more reliable, scalable, and secure. So we're going to look at a couple of different patterns today. First, starting with data management. So we're going to look at the cache-aside pattern. So this method involves loading data into a cache on demand from a data store. It allows for efficient retrieval of frequently accessed data. The second is sharding. This technique divides a data store into horizontal partitions or shards to improve scalability and performance by distributing data across multiple storage nodes. Valet key, a security approach where clients use a token or key to get restricted access to specific resources or services, ensuring controlled data access. Static content hosting. This practice involves deploying static content like images or web files to a cloud based storage service, allowing clients to access the content directly. So let's take a look at cache aside. Many commercial caching systems provide read through and write through right behind operations. In these systems, an application retrieves data by referencing the cache. If the data isn't in the cache, it is retrieved from the data store and added into the cache. Any modifications to the data held in the cache are automatically written back to the data store as well. For caches that don't provide this functionality, it is the responsibility of the applications that use the cache to maintain the data. If an application updates information, it can follow the write-through strategy by making the modification to the data store and by invalidating the corresponding item in the cache. When an item is next required, using the cache aside strategy will cause the updated data to be retrieved from the data store and added back into the cache. So let's take a look at some of the issues and considerations when thinking about the cache aside. So consider the following points when deciding on how to implement this pattern. The life cycle, the lifetime of cache data. Many caches implement an expiration policy that invalidates data and removes it from the cache if it's not accessed for a specified period. For cache aside to be effective, ensure that the expiration policy matches the pattern of access for the applications that are using the data. Don't make the expiration period too short because this can cause the applications to continuously retrieve data from the data store and add it to the cache. Similarity, don't make the expiration period so long that the cache data is likely to become stale. Remember that caching is most effective for relatively static data or data that is read frequently. Evicting data. Most caches have a limited size compared to the data store where the data originates, and they'll evict data if necessary. Most caches adopt a least recently used policy for selecting items to evict, but this might be customizable. Configure the global expiration property and any other properties of the cache and the expiration policy of each cached item to ensure that the cache is cost effective. It isn't always appropriate to apply a global eviction policy to every item in the cache. For example, if a cached item is very expensive to retrieve from the data store, it can be beneficial to keep this item in the cache at the expense of more frequently accessed but less costly items. Priming the cache. Many solutions pre-populate the cache with the data that an application is likely to need as part of the startup processing. The cache aside pattern can still be useful if some of the data expires or is evicted. Consistency. Implementing the cache aside pattern doesn't guarantee consistency between the data store and the cache. Any item in the data store can be changed at any time by an external process, and this change might not always be reflected in the cache until the next time the item is loaded. In a system that replicates the data across the data stores, this problem can become quite serious if synchronization occurs frequently. Local and memory caching. A cache could be local to an application instance and stored in memory. Cache aside can be useful in this environment if an application repeatedly accesses the same data. However, a local cache is private, and so different application instances could each have a copy of the same cache data. This data could quickly become inconsistent between the caches, so it might be necessary to expire data held in a private cache and refresh it more frequently. In these scenarios, consider investigating the use of a shared or a distributed caching mechanism. So, when should you use it? The cache aside pattern, there's a couple of specific scenarios where this pattern is most effective. Firstly, this pattern is ideal when your cache doesn't provide native read-through and read-write operations. In such cases, the cache aside patterns helped in managing the data retrieval and storage processes more effectively. Secondly, when the cache demand is unpredictable, cache aside can be a lifesaver. It allows you to dynamically load data into the cache and as and when needed, ensuring that your application remains responsive and performant, even under varying loads. Thirdly, when the cache data is not set static, this pattern proves beneficial as data changes frequently. The cache aside assures that the cache is updated only when necessary, preventing stale issues and maintaining data consistency. Finally, it's particularly useful when you are not caching session state information in the web application, which is hosted in a web farm. In such environments, managing session state can be challenging, and the cache aside offers a flexible and reliable solution. In summary, cache aside is a powerful pattern for scenarios where native cache operations are lacking, resource demand is unpredictable, and the data set is dynamic or session state caching is not required. Embracing this pattern can significantly enhance the efficiency and scalability of your application. So let's look at an example here. So when an application needs to retrieve data, it will then first search to see if it exists in an Azure cache for Redis. If the data is found in Azure cache for Redis, like the cache is hit, then the application will use this data. If the data is not found in the Azure cache for Redis, so the cache misses, then the application will need to retrieve the data from the appropriate Azure database service. For the cache miss scenario, the requesting application should add the data retrieved from the Azure Database Service into Azure Cache Redis. Let's take a look at sharding. So sharding can help divide a data store into a set of horizontal partitions or shards. This can improve scalability when storing and accessing large volumes of data. The lookup strategy in this strategy and sharding logic implements a map that routes a request for data to the shard that contains the data using a shard key. In a multi-tenant application, all the data for the tenant must be stored together in a shard using the tenant ID as the shard key. Multiple tenants might share the same shard, but the data for a single tenant won't be spread across multiple shards. Another way of looking at it is the RAIN strategy. This strategy groups related items together in the same shard and orders them by shard key. The shard keys are sequential. It's useful for applications that frequently retrieve sets of items using range queries, queries that return a set of data items for a shard key that falls within a given range. For example, if an application regularly needs to find all orders placed in a given month. This data can be retrieved more quickly if all orders for the given month are stored in date and time order in the same shard. If each order was stored in a different shard, they'd have to be fetched individually by performing a large number of point queries, queries that return a single data item. Another strategy is the hash strategy. The purpose of this strategy is to reduce the chance of hotspots, so shards that receive a disproportionate amount of load. It distributes the data across the shards in a way that achieves a balance between the size of each shard and the average load that each shard will encounter. The sharding logic computes the shard to store an item based on the hash of one or more attributes of the data. The chosen hashing function could distribute data evenly across the shards, possibly by introducing some random element into the computation. So let's take a look at some of the issues and considerations when thinking about the shard pattern. So sharding, as many of you may know, is a central technique to ensure scalability and performance in large-scale databases. However, effective sharding requires careful planning and consideration of several factors. Firstly, shard balancing is a fundamental issue. Ensuring that your data is evenly distributed across all your shards is crucial to prevent any single shard from becoming a bottleneck. Proper shard balancing enhances performance and maximizes resource utilization. Secondly, using a stable and unique key data to determine your sharding state is vital. Unique keys ensure that the data is correctly and consistently placed in the appropriate shards, minimizing the risk of data duplication or loss. Thirdly, an efficient query design to query sharding data cannot be overstated. Efficient queries ensure that data is retrieved as fast and reliable, even when spread across multiple shards. A well-designed query system can significantly reduce latency and improve user experience. Additionally, when designing for scalability, both the data and throughput must be considered. This involves planning for the addition of more storage nodes as data grows, ensuring that the system can handle increased load without compromising performance. Lastly, monitoring backup and maintainability and maintaining consistency of multiple shards is an ongoing task that requires continuous attention. Regular monitoring helps identify potential issues before they become critical, while consistent backups ensure that data integrity and availability in the event of failures. In summary, while sharding offers significant benefits for managing large scale databases, it also presents several challenges. Addressing shard balancing, utilizing stable and unique keys, designing efficient queries, planning for scalability, and maintaining robust monitoring and backup processes are all essential considerations for successful sharding. So, when should you use it? The primary focus of sharding is to improve the performance and scalability of a system, but as a byproduct, it can also improve availability. Due to how the data is divided into separate partitions, a failure in one partition doesn't necessarily prevent an application from accessing data held in other partitions, and an operator can perform maintenance or recovery of one of more partitions without making the entire data for an application inaccessible. So consider a website that surfaces an expansive collection of information published books that are worldwide. The number of possible books cataloged into this workload and typical query usage patterns contradict the usage of a single relational database to store the book information. The workload architect decides that to shard the data across multiple database instances using the book's static international standard book number, so ISBN, for the shard key. Specifically, they use the check digit like 0 to 10 of the ISBN that gives 11 possible logical shards, and the data will be fairly balanced across each shard. To start with, they decide to co-locate the 11 logical shards into 3 physical shard databases. They can then use the lookup sharding approach and store the key to server mapping information in a shard database. So let's take a look at the valet key pattern. So data stores have the ability to handle upload and download of data directly without requiring that the application perform any processing to move this data. But this typically requires the client to have access to the security credentials for the store. This can be a useful technique in minimizing data transfer costs and the requirements to scale the application and to maximize performance. It means, though, that the application no longer able to manage the security of the data. After the client has connection to the data store for direct access, the application can't act as the gatekeeper as it's no longer in control of the process and can't prevent subsequent downloads or uploads from the data store. This isn't a realistic approach in distributed systems that need to serve untrusted clients. Instead, applications must be able to securely control access to the data in a granular way, but still reduce the load on the server by setting up the connection and then allowing the client to communicate directly with the data store to perform the required read or write operations. So let's discuss some of the critical issues and considerations required with the valet key pattern and access management systems. The valet key pattern is a powerful approach that grants limited access to resources, but its implementation comes with several important considerations to ensure security and efficiency. Firstly, it's essential to ensure that the token or key used for access is securely generated and transmitted. This is crucial to prevent unauthorized access and maintain integrity of the system. Secure generation and transmission of keys are fundamental to safeguarding sensitive data and resources. Secondly, implement mechanisms to easily revoke access if needed. Access revocation is a vital feature to quickly respond to potential security threats or changes in access requirements. Efficient revocation mechanisms help in maintaining control over who has access to what resources at a given time. Thirdly, the valet key pattern could introduce security and audit risks if not implemented correctly. Proper implementation is necessary to avoid vulnerabilities that could be exploited. Regular audits and security checks are critical to ensure that the system remains robust and secure. Moreover, cost savings from offloading processing must be weighed against the complexity of implementing and managing the valet key pattern. While offloading can lead to significant cost reductions, the additional complexity in managing access keys and permissions must be carefully considered to ensure that it doesn't outweigh the benefits. Lastly, ensure that the resources are managed efficiently to avoid unnecessary costs, especially when dealing with frequent or large client requests. Efficient resource management helps in maintaining performance and reducing operational costs, making the system more scalable and sustainable. In summary, while the valet key pattern offers significant advantages in access management, it's crucial to address security, revocation, and implementation complexity and resource management to fully harness its benefits. By carefully considering these factors, we can build secure, efficient, and cost effective access management systems. So, valet key pattern in specific scenarios where the pattern proves particularly beneficial. The valet key pattern provides a way to grant limited access to resources, and understanding when to use it can greatly enhance the efficiency and security of your applications. Firstly, we should offload data transfer from the application to minimize the use of valuable resources, such as compute, memory, and bandwidth. By using the valet key pattern, we can delegate data transfer tasks to clients, freeing up these crucial resources for other essential operations. Secondly, this pattern helps to minimize operational costs by enabling direct access to stores and queues. Direct access reduces the need for intermediary processing, thereby cutting down the operational overhead and making the system more cost effective. The valet key pattern is especially useful when clients regularly upload or download data, particularly when dealing with large volumes or operations involving larger files. By granting clients direct access, we can streamline those data-intensive processes and improve overall performance. Additionally, it's advantageous when the data is stored in a remote data store or a different data center from the application. In such cases, providing direct access via valet key can significantly reduce latency and enhance data transfer speeds. Lastly, consider using the valet key pattern if the application doesn't need to perform tasks on the data first. When the application does not require pre-processing or validation of the data, direct access can simplify the data flow and reduce unnecessary processing steps. In summary, the valet key pattern is a powerful tool for offloading data transfer, minimizing operational costs, handling large volumes of data, optimizing remote data flows, and simplifying data workflows. So Azure supports shared access signatures on Azure Storage for granular access control to data in blobs, tables, and queues, and for service bus queues and topics. A shared signature token can be configured to provide access rights such as read, write, update, and delete to a specific table, a key range within a table, a queue, a blob, or a blob container. The validity of the token of the access shared access signature can be a specified time period. This functionality is well suited for using a valet key for access. Let's take a look at static content hosting. So web applications typically include some elements of static content. The static content might include HTML pages and other resources such as images and documents that are available to the client, either as part of a HTML page such as inline images, style sheets, and client-side JavaScript files, or a separate download such as a PDF document. Although web services are optimized for dynamic rendering and output caching, they still have to handle requests to download static content. This consumes processing cycles that could often be put to better use. Deploying static content to a cloud-based storage system service that can deliver them directly to the client. This can reduce the need for potential expensive compute instances. So let's take a look at some of the issues and considerations when you're considering static content hosting. So as we move forward in enhancing our digital infrastructure, understanding the issues and considerations related to static content hosting is crucial. Let's dive into several key points. First, we need to recognize that static content may need to be provisioned and deployed independently from the application. It's not included in the application deployment package or process, if it's not. This separation ensures that the updates to static content do not necessitate a full redeployment of the application, thereby improving efficiency and reducing downtime. Next, security access is paramount concern. We must ensure that the public read-write access is restricted to prevent unauthorized uploads. Unauthorized access can lead to malicious content being reintroduced, which can compromise the integrity and security of our applications. Geographic concerns also play a significant role. To address latency and improve load time for users around the globe, we should consider using a content delivery network or CDN. By caching the contents of the storage container in multiple data centers worldwide, we can ensure that users have a faster and more reliable experience. Storage services present another potential challenge. Some services may not support the use of custom domain names, which can be a limitation if branding and domain-specific content delivery are important to your strategy. In terms of performance optimization, file compression techniques such as gzip are essential. Compressing files reduces load time for clients, which is critical in providing a seamless user experience and improving overall site performance. Moreover, we need to consider how to handle local development and testing, ensuring that our development environment mirrors the production environment as closely as possible, which helps in identifying and resolving issues before deployment, thereby reducing the risk of errors. Lastly, caching existing assets is a practice that cannot be overlooked. Proper caching strategies ensure that the frequently accessed content is readily available, reducing server load and speeding up content delivery to users. In conclusion, by addressing these considerations, provisioning and deployment security, geographic distribution, storage limitations, file compression, local development, and caching, we can build a robust and efficient static hosting strategy that will not only improve our application performance, but also ensure a secure and reliable user experience. So, should you use it? So, static content hosting in our fast paced digital world, the efficiency and performance of our web applications are crucial to maintaining user satisfaction and operating and optimizing operational cost. Static content hosting offers a powerful solution that addresses several key challenges in web development and deployment. Firstly, let's take a look about cost reduction. Hosting costs can quickly escalate, especially for websites and applications that include a mix of dynamic and static resources. By utilizing cloud hosted storage for static content, we can significantly reduce these costs. Cloud hosted storage is typically much less expensive than compute instances. By offloading static resources to the cloud, we can allocate our budgets more efficiently, allowing us to invest in other critical areas for our business. Secondly, performance improvement is a major benefit of this approach. By offloading static content serving to specialized storage solutions, we can enhance the performance of our main web application. This means faster load times and a smoother user experience, which is essential for retaining users and maintaining a competitive edge in the market. Furthermore, static content hosting is not just about the cost and performance, it also offers the advantage of exposing static resources and content for applications running in various hosting environments or on-premises servers. This flexibility ensures that our content is accessible from different platforms and infrastructures, providing a seamless experience for users regardless of their location or device. Another significant advantage is improved performance and availability achieved through content delivery networks or CDNs. By caching the content of the storage container in multiple data centers around the world, CDNs ensure that our application is readily available and performs optimally, even during peak traffic times. This global distribution minimizes latency and enhances the overall user experience, which is crucial for maintaining high user engagement and satisfaction. In conclusion, adopting static content hosting is a strategic move that offers numerous benefits from reducing hosting costs and improving performance to enhancing flexibility and availability. By leveraging cloud hosted storage and CDNs, we can ensure that our web applications not only cost effective, but also deliver exceptional performance and reliability. At the core of this process is a seamless interaction between the application, the client, and the storage service. Let's take a look at this. So, application delivery. So, this journey starts with our application, which is responsible for delivering pages containing links of files stored in an Azure storage service. These pages are then sent to the client's browser, paving the way for efficient content delivery. When the client receives these pages, they contain references to various static resources such as style sheets, JavaScript files, documents, and images. The client then initiates requests to the Azure Storage Service to fetch these files. The Azure Storage Service then houses the static resources in organized containers. These containers segregate different types of files such as CSS style sheets, JavaScript files, documents, and images. This organization ensures that the retrieval process is streamlined and efficient. Upon receiving the request from the client, the storage service swiftly delivers the requested files. This mechanism offloads the burden of serving static content from our primary application servers, thereby enhancing the overall performance and responsiveness of our web applications. By leveraging Azure Static Content hosting, we can gain several critical benefits, such as enhanced performance. Offloading static content serving to Azure Storage significantly improves the performance of our main web application. This ensures faster load times and a smoother user experience. Scalability. So Azure Storage Services are designed to scale effortlessly, accommodating growing amounts of static content without compromising on performance or availability. Cost efficiency. So utilizing Azure Storage for static content is very cost effective. It reduces the load of our compute resources, allowing us to manage our budgets more effectively. Reliability and availability. So Azure's global infrastructure ensures that our content is available and delivered efficiently for users across different geographic locations, minimizing latency and enhancing user satisfaction. In conclusion, adopting Azure Static Content Hosting is a strategic move that empowers us to build high performing, scalable, and cost efficient web applications. By offloading static content to Azure Storage, we can focus on delivering dynamic and engaging user experiences without compromising on performance or budget. So let's take a look at design and implementation patterns. So design and implementation of modern applications as we strive to build robust, scalable, and maintainable systems. Understanding and leveraging these strategies is crucial. Let's explore four foundational patterns that I've illustrated here: ambassador, sidecar, leader election, and strangler fig. Firstly, the ambassador pattern involves creating helper services that send network requests on behalf of a consumer service or an application. This pattern simplifies network communication, which can handle various cross-cutting concerns such as logging, monitoring, and retries. Next, we have the sidecar pattern. This involves deploying components of an application into a separate service or container. The primary objective here is to provide isolation and encapsulation, ensuring that auxiliary tasks such as logging, configuration, and networking can be managed independently of the main application logic. The leader election pattern is essential for coordinating the collaboration tasks in a distributed application. By electing one instance as a leader, this pattern ensures that the leader assumes responsibility for managing other instances, facilitating organization and efficient task management. Lastly, the strangler fig pattern offers a prudent approach to incrementally migrating a legacy system. This pattern involves gradually replacing specific pieces of functionality with new applications and services, thereby modernizing the system without disrupting its operation. In conclusion, adopting these patterns, ambassador, sidecar, leader election, and strangler fig, empowers us to design and implement applications that are efficient, scalable, and maintainable. By integrating these strategies, we can build resilient systems that stand the test of time. So let's take a look at Ambassador. So resilient cloud-based applications require features such as circuit breaking, routing, metering, and monitoring, and the ability to make network-related configuration updates. It may be difficult or impossible to update legacy applications or existing code libraries to add these features because the code is no longer maintained or can't be easily modified by the development team. Network calls may also require substantial configuration for connection, authentication, and authorization. If these calls are made across multiple applications built using multiple languages and frameworks, the calls must be configured for each of these instances. In addition, network and security functionality may be needed to be managed by a central team within the organization. With a large code base, it can be very risky for that team to update application code that they aren't familiar with. Client frameworks and libraries Put client frameworks and libraries into an external process that can act as a proxy between your application and the external services. So you can deploy the proxy on the same host environment as your application to allow control over routing, resiliency, security features, and to avoid any host related restrictions. So the ambassador is essentially a proxy acting to really integrate across those multiple different types of applications and services that you might be running with. So when consider implementing the ambassador pattern, let's consider the following issues and considerations. The first is latency overhead. The proxy can add some latency overhead. It's important to evaluate whether a client library, whether it's invoked directly by an application, might be a better approach to avoid this additional latency. So you just need to consider essentially you're adding another service to your application as well. The, the, the proxy can have generalized features. So including generalized features in the proxy can have unintended consequences. For example, the ambassador could handle retries, but this may not be safe unless all operations are idempotent. Ensure that the features implemented in the proxy do not introduce risks or conflict with the application's requirements. Context, context passing. Consider a mechanism to allow the client to pass some context to the proxy and back to the client. For example, include the HTTP request headers to opt out of retry, or specify the maximum number of times to retry. This flexibility can help tailor the proxy's behavior to specific needs. Packaging and deployment. Think about how you package and deploy the proxy. The proxy can be deployed as a sidecar to accompany the lifecycle of the consuming application or service. Alternatively, if an ambassador is shared by multiple separate processes on a common host, it can be deployed as a daemon or a Windows service. Shared versus dedicated instances. So you need to decide whether to use a single shared instance for all clients or an instance for each client. This decision can impact resource utilization, performance, and isolation between clients. Security and configuration. Network calls may require substantial configuration for connection, authentication, and authorization. If these calls are not used across multiple applications built using multiple languages and frameworks, the calls must be configured for each of these instances. Additionally, network and security functionality may need to be managed by a central team within your organization. Specialized team. So features that must be offloaded to the ambassador can be managed independently of the application. This allows for separate specialized teams to implement and maintain security, networking, or authentication features that are being moved to the ambassador without disturbing the application's legacy functionality. By addressing these issues and considerations, you can effectively implement the ambassador pattern to embrace the networking capability, security, and maintainability of your application. The ambassador pattern should be used in the following scenarios where you want to offload common client connectivity tasks. So when you want to offload client common connectivity tasks such as monitoring, logging, routing, security such as TLS, and resiliency patterns in a language agnostic way, legacy applications. So when dealing with legacy applications or other applications that are difficult to modify, the ambassador pattern can extend their networking capabilities without requiring changes to the application code. Specialized teams. You may want to enable a specialized team to implement and maintain security, networking, or authentication features independently of the application. This allows for updates and modifications to the ambassador without disturbing the application's legacy functionality. Resilient cloud-based applications. So when building resilient cloud-based applications that require features such as circuit breaking, routing metering and monitoring, and the ability to make network-related configuration updates, the ambassador pattern can facilitate these features without modifying the existing code base. Centralized management of networking and security. So when network calls require substantial configuration for connection, authentication, and authorization across multiple applications built using multiple languages and frameworks, the ambassador pattern allows these configurations to be managed centrally, reducing the risk of updating the application code by a team that's unfamiliar with it. Standardization and extending instrumentation. So when you need to standardize and extend instrumentation, such as monitoring performance of metrics like latency or resource usage, the ambassador pattern allows this monitoring to happen in the same host environment as the application. So supporting a cloud or cluster connectivity requirements. When you need to support cloud or cluster connectivity requirements in a legacy application or in an application that's difficult to modify, by considering these scenarios, you can effectively use the ambassador pattern to enhance the networking capabilities, security, and maintainability of your applications. So the ambassador pattern specifically uses and Azure solutions. So this pattern plays a pivotal role in simplifying and enhancing the communication between applications and the remote services. So let's dive into the workflow that is illustrated here to understand how the ambassador pattern operates and the benefits it can offer from an Azure perspective. So the journey begins when our application hands a request to a remote service. However, instead of directly communicating with the remote service, the request is now sent via an application proxy. The ambassador proxy, sorry. The ambassador proxy takes on several responsibilities to ensure efficient and secure communication. It determines the location and route request. It first determines the location of the remote services and routes the request appropriately. It checks the circuit breaker state to ensure that the service is available and to prevent overloading. The proxy enriches the request headers with tracing information, which is crucial for monitoring and debugging. It starts measuring the request latency to monitor the performance. The request is then encrypted and sent using a mutual certificate based authentication for enhanced security. The latency of the request is logged for performance analysis. Finally, the ambassador returns a response to the client application. The remote service receives the request, processes it, and sends back the response. The response then travels back through the ambassador proxy before reaching the application. By implementing the ambassador pattern with Azure Solutions, we can reap several significant benefits. The ambassador proxy can handle complex communication logic, allowing the main application to focus on the core functionality. With mutual certificate-based authentication and encryption, the data exchange between the application and the remote service is secure. By enriching headers with the tracing information and logging request latencies, we gain valuable insights into the performance and health of our services. The circuit breaker mechanism ensures that the application remains resilient, preventing it from overwhelming or relying on unavailable services. In conclusion, Adopting the ambassador pattern with Azure solution enhances the security, efficiency, and resiliency of our applications by offloading complex network interactions to the ambassador proxy. We can build their robust, maintainable systems that stand the test of time. So, deploying components of an application into a separate process or container to provide isolation and encapsulation. This pattern can be used to enable applications to be composed of heterogeneous components and technologies. This pattern is named sidecar because it resembles a sidecar attached to a motorcycle. In the pattern, the sidecar is attached to the parent application and provides supporting features for that application. The sidecar also shares the same life cycle as the parent application, being created and retired alongside the parent. This sidecar pattern is sometimes referred to as a sidekick pattern and as a decomposition pattern. So when implementing the sidecar pattern, we need to consider the following issues in consideration. Deployment and packaging. So carefully decide on the deployment and packaging format for our services, processes, or containers. Containers are particularly well suited to the sidecar pattern. Inter-process communication. So choose the inter-process communication mechanism wisely. Aim to use language or framework agnostic technologies unless performance requirements make that impractical. Functionality placement. So before placing functionality into a sidecar, consider whether it would work better as a separate service or a more traditional daemon. Also evaluate if the functionality could be implemented as a library or using traditional extension mechanism, such as language-specific libraries that may offer deeper integration and less network overhead. Resource management. So the sidecar can access the same resources as the primary application, which allows it to monitor system resources used by both the sidecar and the primary application. Latency. Communication between the parent application and a sidecar services includes some overhead, notably latency in the calls. This may not be acceptable trade-off for chatty interfaces. Application size and resource cost. So for small applications, the resource cost of deploying the sidecar service for each instance may not be worth the advantage of isolation. Scaling. So if a service needs to scale differently or independently from the main application, it may be better off to deploy the feature as a separate service. Security. By encapsulating tasks and deploying them out of process, you can reduce the surface area of sensitive processes to only the code needed to accomplish the task. Sidecars can also add cross-cutting security controls to an application component that is not natively designed with that functionality. Operational excellence. So the sidecar pattern provides an approach to implementing flexibility and tool integration that might enhance the application's observability without requiring the application to take direct implementation dependencies. It enables the sidecar functionality to evolve and be maintained independently of the application lifecycle. So performance efficiency. So moving cross-cutting tasks to a single process that can scale across multiple instances of the main process reduces the need to deploy duplicate functionality for each instance of the application. By addressing these issues and considerations, you can effectively implement the sidecar pattern to enhance the modularity, security, and maintainability of your applications. So the sidecar pattern should be used in the following scenarios. Heterogeneous set of languages and frameworks. So when your primary application uses a heterogeneous set of languages and frameworks, a component located in a sidecar service can be consumed by applications written in different languages using different frameworks. The component ownership by remote teams. So when a component is owned by a remote organization or team, so when a component is owned by a remote team or a different organization, this allows the component to be developed and maintained independently of the main application. Co-location requirements. So when a component or feature must be co-located on the same host as the application, this ensures that the component can access the same resources and environment as the primary application. Independent updates. When you need a service that shares the overall lifecycle of your main application but can be independently updated, this allows for flexibility in updating the sidecar without affecting the main application. Fine-grained resource controls. So when you need fine-grained control over resource limits for a particular service or component, for example, you may want to restrict the amount of memory a specific component uses. Deploying the component as a sidecar allows you to manage memory usage independently of the main application. Security enhancements. So when you need to encapsulate tasks and deploy them out of process to reduce the surface area of sensitive processes to only the code needed to accomplish that task. So sidecars can also add cross-cutting security controls to an application component that is not natively designed with that functionality. Operational excellence. So when you want to implement flexibility and tool integration that might enhance the application's observability, but without requiring the application to take direct implementation dependencies, the sidecar functionality can evolve and be maintained independently of the application's lifecycle. Performance efficiency. So when you want to move cross-cutting tasks to a single process that can scale across multiple instances of the main process, reducing the need to deploy duplicate functionality for each instance of the application. By considering these scenarios, you can effectively use the sidecar pattern to enhance the modularity, security, and maintainability of your applications. So let's take a look at a common sidecar pattern example here. So here we can use the Open Telemetry Collector as a sidecar container. So using a sidecar container that enhances the application with the required SSL functionality, but without having to modify the application code. The sidecar pattern is a powerful concept in container-based architectures that lets you decompose application functionality into different container images that can run together in the same container group. It's an In this example, it's an Azure Container Instance container group. Each container can take over part of the functionality of the application requires. The sidecar containers can then use different container images from the application container, even from different image repositories. Containers in the same container group share the same properties, such as the underlying networking stack. So let's take a look at leader election. So a typical cloud application has many tasks acting in a coordinated manner. These tasks could be all instances running the same code or requiring access to the same resources, or they might be working together in parallel to perform the individual parts of a complex calculation. The task instances might run separately for much of the time, but it might also be necessary to coordinate the actions of each instance to ensure that they don't only conflict but cause contention for shared resources or accidentally interfere with the work that other task instances are performing. For example, in a cloud based system that implements horizontal scaling, multiple instances of the same task could be running at the same time, with each instance serving as a different user. If these instances write to a shared resource, it's necessary to coordinate the actions to prevent each instance from overwriting the changes that are made by the others. If the tasks are performing individual elements of a complex calculation in parallel, the results need to be aggregated when they all complete. Coordinate the actions performed by a collection of collaborating instances in a distributed application by electing one instance as a leader that assumes responsibility for managing the others. This can help to ensure that the instances don't conflict with each other, causing contention for shared resources or inadvertently interfere with the work that the other instances were performing. So when implementing the leader election pattern, consider the following issues and considerations. Preventing multiple leaders. So ensure the election process is managed carefully to prevent two or more instances from taking over the leader position simultaneously. This requires a robust mechanism for selecting the leader that can handle events such as network outages or process failures. Failure detection. The system must be able to detect when the leader has failed or become unavailable, i.e., due to communications failure. The speed of detection depends on the system requirements. Some systems can tolerate a short period without a leader, while others need immediate detection and a new election. Handling leader termination. So in systems with horizontal scaling, the leader could be terminated if the system scales back and shuts down some computing resources. Ensures that the system can handle such scenarios and elect a new leader promptly. Avoiding single points of failure. So using a shared distributed um, infrastructure introduced a dependency on an external service which provides the mutex which can become a single point of failure. If this service becomes unavailable, the systems won't be able to elect a leader. So the leader is a bottleneck. Avoid making the leader a bottleneck in the system. The leader's role is to coordinate the work of subordinate tasks, not necessarily to participate in the work itself. Ensure that the leader can delegate tasks effectively to avoid performance issues. So, latency and performance. The resulting latency from leader coordination can affect the performance and response times of other processes if they are waiting for the leader to coordinate and operate. Optimize the leader election process to minimize latency. Flexibility and optimization. So, implementing leader election algorithms manually provides the greatest flexibility for tuning and optimizing the code. However, this approach requires careful design and testing to ensure robustness. Election algorithms. So, consider using established leader election algorithms such as the bullet algorithm or the ring algorithm. These algorithms assume that each candidate in the election has a unique ID and can communicate reliably with other candidates. Coordination requirements. So use the leader election pattern when tasks in a distributed application need careful consideration and there's no natural leader. This pattern is useful for cloud hosted solutions where multiple instances need to work together without conflict. Alternative solutions. So evaluate if a more lightweight method such as optimistic or pessimistic locking can achieve the required coordination. Also consider third-party solutions like Apache Zookeeper for managing a leader election and coordination tasks. By addressing these issues and considerations, you can effectively implement the leader election pattern to ensure reliable and efficient coordination in distributed systems. So the leader election pattern should be used in the following scenarios. Task coordination. So when you need to coordinate a task among multiple instances of a service or application, the leader election pattern ensures that one instance acts as a coordinator, preventing conflicts and ensuring smooth operation. Avoiding single points of failure. So when you want to avoid having a single point of failure in an application, by using leader election, if the current leader fails, a new leader is automatically selected, ensuring continuous operation without manual intervention. Distributed systems. In distributed systems where multiple instances need to work together without conflict, the leader election pattern helps in managing and coordinating tasks effectively across the different instances. High availability requirements. So when your application requires high availability and resilience, the pattern helps maintain service continuity by electing a new leader if the current one fails, thus supporting failover mechanisms. Scalability. When you need to scale out your application horizontally, the leader election pattern can help manage the coordination of tasks across multiple instances, ensuring that the system scales efficiently without bottlenecks. Consensus algorithms. So, implementing consensus algorithms to manage failover and ensure that work is reliably redirected in case of node malfunctions. This is particularly useful in scenarios where reliability and self-healing are critical. Using off-the-shelf solutions. So when you prefer not to implement a leader election algorithm from scratch, off-the-shelf solutions such as Apache Zookeeper can be used to manage leader elections and coordination tasks efficiently. By considering these scenarios, you can effectively use the leader election pattern to ensure reliable and efficient coordination and distributed systems, enhancing the overall resilience and scalability of your application. So, leader election is an essential pattern in distributed systems architecture. Leader election specifically using Azure solutions. So this pattern plays a critical role in ensuring the smooth and coordinated operation of distributed systems by designing a single leader to manage the specific tasks and responsibilities. Let's explore the workflow that's depicted in this diagram to understand how leader election works and the advantages it offers. So replica initialization. In a distributed system, multiple replicas, so replica 1, replica 2, replica 3, all perform various tasks. Initially, these replicas can be in a state where they can become the leader. So the leader election process. So the current leader, at any given moment, one replica is designated as the current leader. In this example, replica 1 is the current leader. A lock mechanism is employed to manage and record the leadership status. This lock contains information such as the current leader, the last observed time, and the lease duration. The current leader, replica 1, updates the timestamp every 10 seconds to maintain its leadership status. This process is known as the heartbeat. Other replicas, such as replica 2 and replica 3, continuously poll the lock to check the leadership status. They monitor the last observed time and the lease duration to determine if the current leader is still active. If the current leader fails to update the timestamp within a specified lease duration, the other replicas recognize that the leader is no longer active. A new leader is then elected from the remaining replicas, ensuring that the system continues to operate smoothly without any single point of failure. By implementing the leader election pattern with Azure Solutions, we gain several significant benefits, such as coordinated tasks benefits. The leader coordinates the actions of the replicas, ensuring that the tasks are managed efficiently and without conflict. The system remains resilient as leadership can be transferred seamlessly in the case of failures. This ensures continuous operation and high availability. This pattern supports scalability, allowing additional replicas to be added without disrupting the existing leadership and coordination mechanisms. By maintaining a single leader, we ensure that decisions and actions are consistent across the distributed system, preventing inconsistencies and conflicts. In conclusion, adopting the leader election pattern enhances the reliability, fault tolerance, and scalability of our distributed systems. So, incrementally migrating a legacy system by gradually replacing specific pieces of functionality with new applications and services. Pattern is called Strangler Fig. As the features from the legacy system are replaced, and the new system eventually replaces all of the old system's features, strangling the old system and allowing you to decommission it. As systems age, the development tools, hosting technologies, and even systems architecture they were built on can become increasingly obsolete. As the new features and functionality are added, the complexity of those applications can increase dramatically, making them harder to maintain or add new features to. Completely replacing a complex system can be a huge undertaking, Often you will need gradual migration to a new system while keeping the old system to handle features that haven't been migrated yet. However, running two separate versions of an application means that the clients have to know where the particular features are located. Every time a feature or service is migrated, clients need to be updated to point to the new location. The Strangler fig pattern does not typically involve the lift and shift or lift and transform approach. Instead, it focuses on incrementally migrating a legacy system by gradually replacing specific pieces of functionality with new application and services. Here are some key points. Incremental migration. So the Strangler fig pattern involves gradually replacing parts of the legacy system with new services. This allows for a controlled and step-by-step transition rather than a wholesale move. Facade later. A facade intercepts requests to the legacy system and routes them either to the legacy applications or the new services. This ensures that the consumers can continue using the same interface without being aware of the migration. Gradual replacement. So as features from the legacy system are replaced, the new system eventually takes over all functionalities, allowing the legacy system to be decommissioned. This approach minimizes risk and spreads the development effort over time, avoiding big bang rewrites. So the pattern supports an incremental approach, avoiding the risks associated with a big bang rewrite. It allows for adding functionality to the new system at a manageable pace while ensuring the legacy application continues to function. In summary, the Strangler fig pattern is about incremental and controlled migration rather than a direct lift or shift and transform approach. It allows for a gradual transition, ensuring continuity and minimizing risks during the migration process. So, when implementing the Strangler fig pattern, we need to consider the following issues and considerations: handling services and data stores. So we need to ensure that both the new and legacy systems can access shared data and shared services and data stores. This is crucial for maintaining consistency and avoiding data integrity issues during the migration projects. Structuring the new applications. So structure new applications and services in a way that can be easily intercepted and replaced in future migrations. This helps maintaining flexibility and ease of further transitions. Facade management. The facade, the facade which intercepts requests and routes them to either legacy or new systems must keep up with migration. It should not become a single point of failure or performance bottleneck. Proper management and monitoring of the um, facade are essential to ensure smooth operation. Incremental migration. This pattern supports incremental migration, which helps to minimize risks, spread the development effort over time. However, this requires careful planning to ensure that each increment is functional and does not disrupt the overall system. Client updates. So running two separate versions of an application means that the clients need to be updated to know where the particular features are located. This can add complexity to the migration processes, as each client must be aware of the changes and adapt accordingly, avoiding single points of failure. Ensuring that the facade does not become a single point of failure, it should be designed to handle high availability and failover scenarios to maintain system reliability during the migration. Performance consideration. The facade could not become a performance bottleneck. It must be capable of handling the load and routing requests efficiently to avoid degrading the user experience. At some point when the migration is complete, the strangle of fig facade will either go away or evolve into an adapter for legacy clients. Plan for this transition to ensure that the final system is clean and does not retain unnecessary components. By addressing these issues and considerations, we can effectively implement the Strangler fig pattern to ensure a smooth and controlled migration from a legacy system to a new architecture. The Strangler fig pattern should be used in the following scenarios. Gradual migration. So when we need to incrementally migrate a legacy system to a new architecture, this pattern allows us to gradually replace specific pieces of functionality with new application and services, minimizing risks and spreading the development effort over time. Complex systems. So, when dealing with complex systems where a complete replacement would be a huge undertaking, the Strangler fig pattern enables a controlled decomposition of a monolith into a set of microservices, allowing the legacy system to continue functioning while new features are added to the new system, maintaining functionality. So, when it's essential to keep the legacy system operational during the migration, the the facade in the Strangler fig pattern intercepts the requests and routes them to either a legacy application or new services, ensuring that the consumers can then continue using the same interface without being aware of the migration. Avoiding Big Bang rewrites. So, when you want to avoid risks associated with a Big Bang rewrite, the Strangler fig pattern supports an incremental approach, allowing you to add new functionality to the new system at your own pace, while ensuring the legacy application continues to function. When modernizing legacy systems that have become increasingly obsolete due to outdated development tools, hosting technologies, or system architectures, this pattern helps in gradually transitioning to a new system while maintaining the old system or features that haven't been migrated yet. When you want to leverage modern orchestration tools such as Azure DevOps to manage the lifecycle of each service, once the application has been decomposed into constituent microservices, these tools can be used to manage the new system effectively. By considering these scenarios, you can efficiently use the Strangler fig pattern to ensure uh, to ensure a smooth and controlled migration from a legacy system to a new architecture, enhancing the overall reliability and scalability of your application. So the Strangler fig pattern provides incremental strategy to migrate legacy systems by gradually replacing pieces of functionality with new applications and services, which ensures a smooth and risk-adverse transition. So let's explore the workflow and the benefits of the Strangler fig pen just a bit more. So on the left, we can see the IBM mainframe, which represents a typical legacy system with various components. So terminals and networking, transaction managers, database and files, core facilities such as scheduling, FTP, printing. So when we start to look at incremental migration, the Strangler fig pattern facilitates a step-by-step replacement of these legacy components. So, so sorry. So in this case, like if we look at the database and files area, we can see that the IBM DB2 and FTP are replaced with modern relational databases like SQL Server, messaging systems such as Service Bus, binary and non-binary file storage such as Azure Storage Services, and event management. Throughout the process, data replication and integration are handled to ensure consistency and minimize downtime. The host integration server facilitates the seamless transition and coexistence of the legacy and new systems during the migration. By leveraging the Strangler fig pattern, you can you can do risk mitigation by gradually replacing legacy components, which reduces the risk associated with large scale migrations. The legacy system continues to operate while new functionality is introduced, ensuring uninterrupted services. Modern application services on Azure offer enhanced scalability and flexibility, and this approach allows us to modernize our infrastructure incrementally, adopting new technologies without disrupting existing operations. In conclusion, The strangle or fig pattern offers a strategic and effective way to modernize our legacy systems by incrementally migrating functionalities. We can achieve a seamless transition to a modern, scalable, and efficient system. So, effective messaging patterns are essential for building scalable, reliable, and efficient distributed systems. Let's delve into four key messaging patterns: sequential Covey, queue-based local load leveling, publisher, subscriber, and asynchronous request reply. So the sequential, lots of talking today. Sequential Covey pattern is designed to process a set of related messages in a defined order without blocking the processing of other groups of messages. This pattern ensures that messages need to be processed sequentially are handled correctly, maintaining the necessary order and coherence in the workflow. So queue-based leveling. So next we have the queue-based leveling pattern. This pattern uses a queue as a buffer between a task and a service that it invokes. By doing so, it smooths out intermittent heavy loads, ensuring that spikes in demand do not overwhelm the system. This approach helps maintain consistent performance and reliability even during peak times. The publisher subscriber pattern enables an approach to announce events to multiple interested consumers asynchronously without coupling the senders to the receivers. This decoupling allows for greater flexibility and scalability as new subscribers can be added without modifying the publisher. This pattern is particularly useful for event-driven architectures where multiple components are needed to react to the same events. Lastly, the asynchronous request reply pattern decouples back-end processing from front-end hosts. In this pattern, back-end processing needs to be asynchronous, but the front end still requires a clear response. By leveraging asynchronous communication, the pattern enhances responsiveness and scalability while ensuring that the front end receives the necessary information. By implementing these messaging patterns, we can achieve several significant benefits. Scalability. So these patterns help manage varying loads efficiently, ensuring that the system scales seamlessly to handle increased demand. Reliability. By decoupling components and handling messages asynchronously, we can build more resilient systems that continue to operate smoothly, even when individual components fail or experience delays. Flexibility. Decoupling senders and receivers allows us to modify components without disrupting the overall system, making it easier to adapt to changing requirements and technologies. Efficiency. So these patterns optimize the processing of messages, ensuring that the resources are used effectively and that the system remains responsive. In conclusion, adopting these messaging patterns, sequential Covey, queue-based load balancing, publisher, subscriber, and asynchronous request to reply empowers us to build robust, scalable, and efficient distributed systems. By leveraging these patterns, we can create architectures that are well equipped to handle the complexity of modern applications. So let's delve into the sequential Covey. So the sequential Covey pattern helps process a set of related messages in a defined order without blocking processing of other groups of messages. So applications often need to process a sequence of messages in the order they arrive, while still being able to scale out to handle increased load. In a distributed architecture, pre-processing these messages in order is not straightforward because the workers can scale independently and often pull messages independently, push related messages into categories within the queuing system, and have the queue listeners lock and pull only from one category, one message at a time. So the sequential Covey pattern is designed to process a set of related messages in a defined order without blocking the processing of other groups of messages. Here are some issues and considerations associated with this pattern. So message queuing. So ensure that the messages are processed in the order that they arrive can be challenging in a distributed architecture. Workers can scale independently and often pull messages independently, which can disrupt the order of processing. Scalability. While this pattern allows for scaling out to handle increased load, it requires careful management to ensure that the order of messages is maintained. This can involve categorizing related messages within the queuing system and having queue listeners lock and pull only from one category at a time. Complexity in implementation. So, implementing this sequential Covey pattern can be complex, especially when dealing with interleaved transactions from multiple orders. The system must be designed to handle these transactions in a first in, first out manner at the order level. Resource management. So, efficiently managing resources to ensure that the processing of one group of messages does not block others is crucial. This involves coordinating actions across distributed services and remote resources. Error handling. So, handling errors in a sequential processing system can be more complex. If an error occurs, the system must ensure that subsequent messages are not processed until the error is resolved, which can involve implementing compensating transactions or other error recovery mechanisms. By addressing these issues and considerations, the sequential Covey pattern can be effectively implemented to ensure order processing of related messages in a distributed system. The sequential Covey pattern should be used in the following scenarios. Order message processing. So when you have messages that arrive in a specific order and must be processed in that same order. This is crucial for maintaining the integrity and consistency of the operations being performed. Categorized messages. So when arriving messages can be categorized in a way that the category becomes a unit of scale of the system. For example, in an order tracking system, messages can be categorized by order ID, ensuring that all the operations related to that specific order are processed sequentially, avoiding blocking. So when you need to process a set of related messages in a defined order without blocking the processing of other groups of messages, this allows for efficient handling of multiple message groups concurrently while maintaining order within each group. However, this pattern might not be suitable for extremely high throughput scenarios, i.e., millions of messages per minute or seconds, as the first in, first out requirement limits the scaling that can be done by the system. Just making sure, I think. Right, let's go through an example of message. This could be a pivotal messaging pattern in distributed systems architecture. So the sequential Covey pattern, specifically using Azure solutions, like this pattern is essential for processing related messages in a defined pattern, ensuring the sequence is preserved without blocking the processing of other message groups. So let's delve into this workflow and benefits as depicted in this diagram. So in our system, we have multiple message senders. Each sender generates messages that are grouped by session IDs. For instance, message with session ID 1000 and session ID 2000 is sent into the system. These session IDs are crucial for maintaining the order of messages within each session. The messages from the different sessions are then routed into a service bus queue. The queue acts as a holding area where messages are stored until they are processed. It ensures that the messages are kept in the order that they arrive, which is essential for preserving the sequence within each session. So, message processing. When a message arrives in a queue, a logic app is triggered. The logic app is responsible for running and processing all the messages in the corresponding session, one at a time, in their arrival. Here's how it works. So, session ID 1000. The logic app processes all the message in the session ID 1000 in the exact order that they arrive. This ensures that the sequence is preserved. Similarity, the logic app processes all messages and session ID 2000 in the arrival order, maintaining the sequence. Each session is processed independently and sequentially, ensuring that the integrity of the message order within each session is maintained. By implementing the sequential Covey pattern, we can achieve some of the significant benefits, such as order preservation. The primary advantage is to ensure that the messages arrive within each session are processed in the exact order that they arrive, which is critical for workloads that depend on message sequence. This pattern allows multiple sessions to be processed concurrently without blocking each other. As a result, the system can handle a higher volume of messages efficiently. Microsoft Azure's robust infrastructure supports scalable processing, allowing the system to handle increasing loads by distributing the processing across multiple instances. Azure Service Bus provides reliable message queuing and delivery, ensuring that no messages are lost and that the order is consistently maintained. In conclusion, adopting the sequential Covey pattern empowers us to build solutions that require strict order processing while maintaining high efficiency and scalability. By leveraging Azure's powerful messaging and processing capabilities, we can create robust and reliable systems that meet the demands of modern applications. So let's take a look at queue-based load leveling. So use a queue that acts as a buffer between a task and a service it invokes in order to smooth intermediate heavy loads that could cause a system to fail or the task to time out. This can help minimize the impact of peaks in demand on availability and responsiveness of both the task and the service. Many solutions in the cloud involve running tasks that invoke services. In this environment, if a service is subjugated to intermittent heavy loads, it can cause performance or reliability issues. A service could be part of the same solution as a task that uses it, or it could be a third party service providing access to frequently used resources, such as a cache or a storage service. If the same service is used by a number of tasks running concurrently, it can be difficult to predict the volume of requests in the service at the time. A service might experience peak in demand that causes it to overload and be unavailable to respond to requests in a timely manner. Flooding a service with a large number of concurrent requests can also result in the service failing if it's unable to handle the contention these requests cause. So we need to think about refactoring a solution and introduce a queue between the tasks and the service, which is where queue-based leveling pattern comes into play. So the queue-based leveling pattern is designed to handle intermediate heavy loads by using a queue as a buffer between a task and the service it invokes. Here are some of the issues and considerations associated with this pattern. So rate control. It's necessary to implement application logic that controls the rate at which the service handle messages to avoid overwhelming the target resource. This involves ensuring that spikes in demand are not passed on to the next stage of the system. Testing under load. So the system should be tested under load to ensure that it provides the required leveling. Adjustments may be needed from number of queues and the number of service instances that handle messages to achieve optimal performance. Scalability. So this pattern can help maximize scalability because both the number of queues and the number of services can be varied to meet demand. However, careful management is required to ensure that the system scales effectively without introducing bottlenecks. This pattern can also help to maximize availability because delays in services won't have an immediate and direct impact on the application. The application can continue to post messages to the queue even when the service isn't available or isn't currently processing messages. Cost control. So the number of service instances deployed only needs to be adequate to meet the average load rather than the peak load, which can help control costs. However, this requires careful monitoring and adjustments to ensure that the system remains cost effective while meeting performance requirements. Throttling. Some services implement throttling where demand reaches a threshold beyond which the system could fail. Implementing load leveling with these services can ensure that this threshold isn't reached, thereby maintaining service functionalities. Temporal coupling. A message broker provides temporal coupling, meaning the producer and consumer do not have to run concurrently. This allows the producer to send messages sorry, this allows the producer to send messages regardless of the consumer's availability, and the consumer can process the request at its own pace. Asynchronous processing. So, this pattern supports asynchronous processing of messages, which can help maintain the responsiveness of the user interface and distribute processing across multiple servers to improve throughput. By considering these issues and implementing appropriate strategies, the queue-based load leveling pattern can effectively manage load and improve the resilience and scalability of the system. The queue-based load leveling pattern should be used in the following scenarios: handling intermediate heavy loads. So when a feature is subjected to intermittent heavy loads that can cause performance or reliability issues, this pattern helps to smooth out these loads using a queue as a buffer between the task and the service it invokes. When you need to decouple tasks from services to allow the service to handle messages at its own pace, regardless of the volume of requests from concurrent tasks, this ensures that the service not only is overwhelmed by the sudden spike in demand, maximizing availability. So, when you want to ensure that delays in service do not have an immediate and direct impact on the application can continue to post messages to the queue even when the service isn't available or isn't currently processing messages. Maximizing scalability. So, when you need to scale both the number of queues and the number of services to meet demand, this pattern allows for flexible scaling to handle varying loads. Cost control. So when you want to control costs by deploying a number of service instances that only need to be adequate to meet the average load rather than the peak load. By using queue-based load leveling pattern in these scenarios, you can improve the resilience, scalability, and cost effectiveness of your system. So queue-based load leveling pattern plays a crucial role in managing varying loads efficiently, ensuring that spikes in demand do not overwhelm the system and maintain consistent performance. So let's explore the workflow and benefits a bit more. So within this diagram, we can see we have multiple app service instances. These instances represent various components of an application that generate tasks or messages to be processed. These instances may experience fluctuating loads with peaks and troughs in demand. The messages from these app service instances are then sent to a service bus queue. The service bus queue acts as a buffer, smoothing out the intermittent heavy loads by holding the messages until they can be processed. This buffering mechanism ensures that the back-end systems are not overwhelmed by sudden spikes in demand. On the right-hand side of the diagram, we can see we have got a function app that processes the messages from the service bus queue. The function app retrieves the messages from the queue and performs the necessary operations on them. After processing, the function app stores the results in a data store. This could be a database, file storage, or any type of persistent storage. So the service bus queue acts as a buffer, smoothing out the peaks and troughs in demand. This ensures that the backend systems are not overwhelmed by the sudden spikes in load, leading to a more consistent, reliable performance. This pattern decouples the message generation from the message processing. The app services instances can continue to generate messages at varying rates without being directly tied to the processing speed of the backend system. By using a queue, messages are reliably stored until they can be processed. This ensures that no messages are lost even when there are temporary issues with the processing components. The systems can recover gracefully from failures, maintaining high availability and performance and reliability. So, publisher subscriber or PubSub for short enables an application to announce events to multiple interested consumers asynchronously without coupling the senders to the receivers. In cloud-based and distributed applications, components of the system often needs to provide information to other components as events happen. Asynchronous messaging is an effective way to decouple senders from consumers and avoid blocking the sender to wait for a response. An input messaging channel used by the sender packages events into messages using a known message format and then sends these messages via an input channel. The sender in this pattern is also called the publisher. One output messaging channel per consumer. The consumers are known as subscribers, a mechanism for copying each message from the input channel to the output channel for all subscribers interested in that message. This operation is typically handled by an intermediary, such as a message broker or an event bus. So, PubSub or Publisher Subscriber enables an application to announce events to multiple interested consumers asynchronously without coupling the senders to the receivers. So the PubSub pattern or publisher subscriber pattern is a messaging pattern where an application publisher sends messages or events to multiple interested consumers or subscribers asynchronously. So let's consider some issues and considerations with this pattern. So, scalability. So, one of the main challenges is ensuring that the system can scale efficiently as the number of subscribers increases. Each new subscriber typically requires additional resources and potential changes to the application code to handle the new message queue. Message delivery. So, ensuring that messages are delivered to all subscribers reliably and in a timely manner can be complex. Message queues generally aim to deliver messages in a first in, first out manner, but this order is not always guaranteed, especially under high load conditions. Monitoring alerts. So, implementing effective monitoring and alerting mechanisms is crucial to track the performance of message queues, detect stuck messages, and ensure that subscribers are processing messages efficiently. Security. So, ensuring that the messages are encrypted and only authorized subscribers can access them is essential. This ensures implementing robust authentication and authorization mechanisms. Deciding how to handle subscriptions is important. You need to determine whether subscribers can subscribe and unsubscribe at their own pace or an approval mechanism is required. Message duplication. So, handling duplicate messages is necessary because message queues guarantee at least one delivery, which means there's a chance that the message might be delivered more than once. Implementing deduplication mechanisms can help manage this queue. Poison messages. So, managing poison messages, which are messages that are repeatedly fail to be processed, is important. These messages should be moved to a separate poison queue to free up the main queue for other messages. One-way communication. The pub-sub pattern is inherently one-way, meaning that subscribers cannot send acknowledgement or responses back to the publisher. If two-way communication needed, another pattern such as request reply should be implemented. Message expiration. So defining how long messages should remain in the queue before they expire is important. This helps in managing the life cycle of the messages and ensuring that outdated messages do not clog the system. Implementing wildcard subscriptions can allow publishers to subscribe to all topics with a single action, which can simplify the management of multiple topics. By addressing these issues and considerations, the publisher-subscriber pattern can be effectively implemented to enable scalable, reliable, and secure asynchronous communication between publishers and multiple subscribers. So the publisher, subscriber, or pub-sub pattern should be used in some of the following scenarios. Broadcasting information to multiple consumers. So when you need to send the same information to multiple consumers simultaneously, the pub-sub pattern is ideal. This allows a single publisher to broadcast messages to multiple subscribers without needing to send their individual messages to each one. Decoupling senders and receivers. So when you want to decouple the senders of the messages from the receivers, enabling them to operate independently. This is useful in systems where the publisher does not need to know about the subscribers and vice versa. Asynchronous communication. When you need to enable asynchronous communication between different parts of a system, this allows the publisher to send messages without waiting for the subscribers to process them, improving the overall responsiveness and scalability of the system. Event-driven architecture. So when implementing event-driven architectures where components need to react to events as they happen, the pub-sub pattern allows a real-time event propagation to multiple interested parties. Handling real-time notifications. So when you need to provide real-time notifications to multiple subscribers, each such as monitoring systems, alert mechanisms, or live data feeds. Scalability and flexibility. So when you need a scalable and flexible system where new subscribers can be added without modifying the publisher, this allows the system to grow and adapt to new requirements easily. Filtering and routing messages. So when you need to filter and route messages to specific subscribers based on certain criteria, this can be achieved using topics and content filtering mechanisms. By using the publisher subscriber pattern in these scenarios, you can create a robust, scalable, and flexible messaging system that efficiently handles communication between different components. Modern distributed systems architecture, such as the publisher subscriber pattern, is crucial for building scalable, decoupled system that efficiently can handle events and messages across various components. So let's explore our workflow and benefits a bit more of the pub-sub pattern as we can see in this diagram. So on the left-hand side, we have the client applications that interact with the system via HTTP. These HTTP applications are authenticated using Microsoft Entra ID, ensuring secure access to the system. The authenticated requests from client applications are routed through an API gateway. The API gateway handles request routing, composition, and other tasks such as rate limiting and security enforcement. Within the workflow, the orchestration layer, logic apps are used to define and automate workflows. Logic apps can receive HTTP requests and orchestrate various backend tasks. So let's take a look at the service bus and event grid. So this layer includes a service bus and event grid, but both play a pivotal role in the pub-sub pattern. So the service bus acts as a message broker, facilitating the asynchronous replication between different components by queuing the messages. The event grid then handles the event-driven communication, enabling the system to react to events as they occur. It efficiently routes events to multiple subscribers, ensuring that all interested parties receive the relevant information. On the right-hand side, we have the various backend services that integrate with the workflow and the orchestration layer, such as SaaS services, so software as a service offerings that can provide various functionality, native Azure services that offer a wide range of capabilities, message-based services that rely on message-based communication, such as Azure Service Bus for reliable messaging, REST and SOAP-based web services that can be evoked as part of the workflow. So by implementing the publisher subscriber pattern with Azure services, we can achieve significant benefits. So the pub-sub pattern decouples the producers from messages, publishers from the consumers, which are the subscribers. This allows for greater flexibility Scalability, as new subscribers can be added without modifying the publishers. So in modern application development, it's normal for client applications, often code running through a web client, as in the browser, to depend on remote APIs to provide business logic and compose functionality, in most cases APIs for a client. So network infrastructure is largely out of the control of the application developer. Most APIs can respond quickly enough for responses to arrive back over the same connection. Application code can make a synchronous API call in a non-blocking way, giving the appearance of asynchronous processing, which is recommended for I/O-based operations. In some scenarios, however, the work is done by the backend may be long-running on the order of seconds, or might be a backend process that is executed in minutes or even hours. In that case, it isn't feasible to wait for the work to complete before responding to the request. This situation is a potential problem for any synchronous request reply pattern because the applications are designed to respond quickly in the order of 100 milliseconds or less. One solution to this pattern is to use HTTP polling. So polling is useful to client-side code, but it can be hard to provide callback endpoints or even long-running connections. Even when callbacks are possible, the extra libraries and services that are required can sometimes add too much extra complexity. So the asynchronous request reply pattern is used to decouple backend processing from a front-end host, where backend processing needs to be asynchronous, but the front end still needs a clear response. Here are some issues and considerations that we can consider when we're looking at the asynchronous request reply pattern: latency and response time. So the pattern is designed to handle scenarios where backend processing is long running. However, this introduces latency in the response time as the client has to poll for the result of the long running operation. This can affect the user's experience if not managed properly. Polling mechanisms. So implementing an efficient polling mechanism is crucial. The HTTP 202 response should indicate the location and frequency that the client should poll for the response. This helps in managing the load of the server and ensures that the client does not overwhelm the server with frequent polling requests. Handling running operations. So the backend must be capable of handling long running operations efficiently. This includes offloading processes to another component, such as a message queue, and ensuring that the status endpoint can accurately reflect the progress of the operation. Proper error handling mechanisms need to be in place if an error occurs during processing. The error should be persistent at a resource URL described in the location header, and the appropriate response called HTTP 4.0 should be returned. This ensures that the client is aware of any issues and can take appropriate action. Status code and redirects. So the API should return the correct status codes based on the state of the operation. For example, upon successful processing, the API should return HTTP 200, which is okay, HTTP 201 created, or HTTP 204 no content. If the status endpoint redirects on completion, HTTP 302 or HTTP 303 should be used. Client-side considerations. So the client-side code must be designed to handle asynchronous responses. This includes managing the polling logic, handling different status codes, and updating the user interface based on the progress and completion of the operation. This pattern allows the client process and backend APIs to scale independently. However, this separation also brings additional complexity when the client requires success notifications as the step needs to become asynchronous. Security. So ensuring secure communication between the client and the server is essential. This includes validating both the request and the action to be performed before starting the long-running process and ensuring that sensitive data is protected during transmission. Some legacy clients may not support this pattern. It is important to consider the compatibility of the pattern with existing clients and whether additional support for alternative solutions are needed to support those clients. Efficiently managing resources such as message queues and status endpoints is crucial to prevent resource exhaustion and ensure that the system can handle a large number of concurrent requests. By addressing these issues and considerations, the asynchronous request reply pattern can be effectively implemented to handle long running operations while providing a clear response to the client. The asynchronous request reply pattern should be used in some of the following scenarios: long running background operations. So, when the background processing is a long running process taking seconds, minutes, or even hours, it's not feasible to keep the client waiting for the operation to complete. This pattern allows the client to initiate the request and then poll for the result later. Decoupling front-end and back-end. When you need to decouple the front-end host from the back-end processing, this is useful in scenarios where the front-end needs a clear response, but the back-end processing needs to be asynchronous. Scalability. So when you want to enable the client process and the back-end APIs to scale independently, by using Message Broker to separate the request and the response stages, you can achieve better scalability and manage load more effectively, handling high latency. So when factors such as network infrastructure, geography, location, or current load and significant latency to the current load can add significant latency to the response. This pattern helps mitigate the issues by allowing the backend to process the request asynchronously and the client to poll for the results. When implementing microservices architecture where the server-to-server REST API calls are common, this pattern helps manage long-running operations and decouple services, making the system more reliable and resilient and scalable. Client-side polling. When it's difficult to provide callback endpoints or long-running connections on the client side, the pattern allows the client to poll for the results, which can be simpler and more efficient for certain scenarios. By using the asynchronous request reply pattern in these scenarios, you can effectively manage long running operations, improve scalability, and decouple front end and back end processing, leading to a more robust and responsive system. So let's take a look at a robust architecture designed to handle long running tasks without blocking client application. So this solution is particularly beneficial for scenarios where immediate response is not feasible, enabling a seamless and responsive user experience. So let's break down this process by the illustrated diagram. So the journey begins when the client application initiates a request by calling an API. This call signifies the commencement of a task that may take an extended period to complete. Immediately after the API call, the request is encapsulated in a message and placed in a queue. This queuing mechanism ensures that the request is safely stored and can be processed asynchronously. Once the message is enqueued, the system promptly replies to the client with a status endpoint. The endpoint allows the client to periodically check the status of the request without being left in the dark. On the processing side, a service continuously monitors the queue and receives a message when it is its turn to be processed. This decoupled mechanism ensures that the processing workflow is evenly distributed and managed effectively. The received message is then processed. Upon completion of the task, the result is written to a storage blob. This step is crucial as it ensures the results are stored in a durable and retrievable manner. At any point, the client can then call the status endpoint to check the progress of the request. This call provides real-time updates, keeping the client informed about the current state of their task. Finally, the client checks the storage blob for the completion status and the results of the task. Once the result is available in the blob, the client can then retrieve and utilize it as needed. This architecture exemplifies the power and flexibility of Azure's asynchronous processing capabilities. By decoupling the request handling from the processing, we achieve not only the efficiency, but also enhance the scalability and reliability of our applications. So, an essential aspect of modern architecture design is reliability. Ensuring your applications are reliable is paramount in delivering a seamless and dependable user experience. To achieve this, we employ several robust patterns and practices, each of which play a crucial role in maintaining the stability and resiliency of our applications. So, let's dive into these key reliability patterns. Circuit breaker. So the circuit breaker pattern is designed to handle faults that may take an indeterminate amount of time to recover from, especially when connecting to remote resource services or resources. By implementing a circuit breaker, we can prevent repeated failures by overwhelming our system. This pattern improves the stability and resiliency of our application by detecting failures and encapsulating the logic of preventing a failure from constantly reoccurring. Essentially, it breaks the circuit to stop the flow of requests to a failing service, allowing it time to recover. Deployment stamps. So the deployment stamp pattern involves provisioning, managing, and monitoring a heterogeneous group of resources to host and operate multiple workloads or tenants. This approach ensures that each group or stamp can be managed independently, providing scalability and redundancy. By isolating workloads, we minimize the risk of a single failure impacting the entire system, thereby enhancing overall reliability. Bulkhead. So in a bulkhead architecture, elements of an application are isolated into pools so that if one fails, the other will continue to function. This pattern is akin to compartmentalizing a ship into watertight sections. If one section floods, the others remain unaffected, keeping the ship afloat. By isolating critical services and resources, we limit the impact of failures and ensure that the rest of the application can continue operating smoothly. Compensating transaction. So the compensating transaction pattern comes into play when one or more steps in a process fail. This pattern allows us to undo the work that the steps performed, effectively rolling back transactions to maintain data consistency. By implementing compensating transactions, we can ensure that our system remains in a consistent state, even if in the face of partial failures, thereby enhancing the reliability of our transactions and our workloads. So these reliability patterns, circuit breaker, deployment stamps, bulkhead, and compensating transaction are fundamental in building resilient applications. They help us manage fault tolerance gracefully, isolate failures, and maintain consistent and reliable operations. By adopting these patterns, we can deliver robust applications that meet the high expectations of our users. So, in a distributed environment, calls to remote resources and services can fail due to transient faults such as slow network connections, timeouts, or the resources being overcommitted or temporarily unavailable. These faults typically correct themselves after a short period of time, and a robust cloud application should be prepared to handle them by using a strategy such as the retry pattern. However, there can also be situations where the faults are due to unanticipated events, and that might take much longer to fix. These faults can range in severity from a partial loss of connectivity to a complete failure of a service. In these situations, it might be pointless for an application to continuously retry an operation that is unlikely to succeed, and instead the application should quickly accept that their operation has failed and handle the failure accordingly. Additionally, if a service is very busy, failure in one part of the system might lead to a cascading failure. The purpose of the circuit breaker pattern is different than the retry pattern. The retry pattern enables an application to retry an operation in the expectation that it'll succeed. The circuit breaker pattern prevents an application from performing an operation that is likely to fail. In the application combine these two patterns by using the retry pattern to invoke an operation through a circuit breaker. However, the retry logic should be sensitive to any exceptions returned by the circuit breaker and abandon retry attempts if the circuit breaker indicates that a fault is not transient. The failure counter used by the closed state is time-based. It automatically resets at a periodic interval. This helps to prevent the circuit breaker from entering the open state if it experiences occasional failures. The circuit breaker pattern is designed to handle faults that may take a variable amount of time to recover from, especially when connecting to remote services or resources. Here are some issues and considerations associated with this pattern. State management. The circuit breaker pattern typically involves three states: closed, open, and half open. Managing these states correctly is crucial. The closed state allows normal operation. The open state immediately fails requests, and the half-open state allows a limited number of test requests to check if the issue has been resolved. Thresholds and timeouts. Setting appropriate thresholds for the number of failures and timeouts is essential. If the thresholds are too low, the circuit breaker might open too frequently, causing unnecessary failures. If they are too high, the system may not protect itself effectively from cascading failures. Recovery testing. In the open state, the circuit breaker should periodically test the service to see if it has recovered. This can be done using a timer or by pinging the service. The interval for these tests should be carefully chosen based on the criticality of the operation and the nature of the service. Manual override. Providing a manual override option can be beneficial in systems where the recovery time for a failing operation is extremely variable. This allows administrators to manually reset the circuit breaker or force it into an open state as needed. Concurrency. The circuit breaker might be accessed by a large number of concurrent instances of an application. The implementation should ensure that it does not block concurrent requests or add excessive overhead to each call. Using a single circuit breaker for multiple underlying independent providers can be problematic. For example, if a data store with multiple shards, one shard might be accessible while another one is experiencing issues. The circuit breaker should be able to differentiate between these resources to avoid unnecessary failures. Accelerated circuit breaking. Sometimes a failure response can provide enough information from the circuit breaker to trip immediately and stay tripped for a minimum period of time. For example, an overloaded shared resource might indicate that an immediate retry is not recommended. Replaying failed requests. In an open state, the circuit breaker should record the details of each failed request and arrange for these requests to be replayed when the service becomes available again. This ensures that important operations are not lost. The circuit breaker might not fully protect applications from operations that fail and external services configured with lengthy timeouts. If the timeout is too long, a thread running the circuit breaker might be blocked for an extended period of time, tying up resources. Aggressive retry policies can also cause an increasing number of transient faults for other users and applications sharing the same resources. It is important to consider the impact of the circuit breaker on a shared resource and other tenants in a multi-tenant environment. By addressing these issues in consideration, the circuit breaker pattern can be effectively implemented to improve the stability and resiliency of an application, preventing cascading failures and managing long-lasting faults efficiently. The circuit breaker pattern should be used in the following scenarios: handling persistent or non-transient errors. When an application encounters persistent or non-transient errors, such as a service being down or a network failure, the circuit breaker pattern can prevent the application from continually trying to perform an operation that is likely to fail, preventing resource exhaustion. So if a service is frequently unavailable or busy, it might be due to resource exhaustion. The circuit breaker pattern helps to prevent further strain on the service by stopping additional requests until the service has had time to recover. improving system stability. This pattern provides stability while the system recovers from a failure and minimizes the impact on performance. It quickly rejects requests from operations that are likely to fail rather than waiting for them to time out or never return. When faults are likely to be long-lasting or terminal, the circuit breaker pattern can handle these faults as exceptions. The application can log the exception and try to continue by invoking an alternative service or offering degraded functionality, avoiding cascading failures. The pattern helps mitigate failures and avoid having cascading failures disrupt the entire application by stopping a request to a failing service. It prevents the failure from propagating to other parts of the system. The circuit breaker pattern allows the application to periodically test a service to detect when it becomes available again. This can be done on an intermediate basis with long intervals between requests, depending on the criticality of the operation and the nature of the service. Logging and monitoring. The pattern can be used to log all failed requests and monitor the health of the operation. This information can be used to alert administrators when the circuit breaker trips to the open state, providing insights on the health of the system. By using the circuit breaker pattern in these scenarios, you can improve the resiliency and stability of your application, prevent resource exhaustion, and manage long-lasting faults effectively. So let's delve into a vital aspect of building resilient cloud applications by looking at the circuit breaker pattern with Azure OpenAI endpoints. So the circuit breaker pattern is a fundamental design principle used to enhance the stability and reliability of distributed systems, particularly when dealing with transient faults or failures in a backend system. So at the core of our architecture, we have a pool of backend services. These services are responsible for handling various tasks and processing tasks from the client application. The pool provides redundancy and load balancing, ensuring the workload is distributed across multiple instances. Under normal conditions, the requests from the clients are routed to the backend services. Each backend instance processes the request and returns the appropriate response. This flow is seamless, ensuring that the system operates efficiently and effectively. Jumping ahead. Efficiently and effectively. So, however, in a real world scenario, backend services may occasionally experience failures or performance degradation. The circuit breaker pattern comes into play precisely at this juncture. When a particular backend instance starts to fail or becomes unresponsive, the circuit breaker detects this anomaly. We can see in this diagram that this is depicted by the middle backend service, which is encapsulated within a red box indicating a fault. The circuit breaker breaks the circuit for this particular instance, preventing any further requests from being routed to it. Instead, the requests are routed to other healthy instances in the pool. While the faulty backend instance is isolated, the circuit breaker provides an opportunity for it to recover. During this time, the remaining backend instances continue to handle the incoming requests, ensuring that the system remains operational. Once the circuit breaker detects that the faulty instance has recovered and is back to normal operation, it closes the circuit, allowing requests to be routed to it once again. This automated handling of faults improves the overall resiliency and stability of the system. In the context of Azure implementation of the circuit breaker pattern, this can be retrieved using various services and tools, such as Azure App Service, Azure Functions, and in this example, Azure API Management allows circuit breaker functionality with Azure OpenAI endpoints. So the deployment stamp pattern involves provisioning, managing, and monitoring a heterogeneous group of resources to host and operate multiple workloads or tenants. Each individual copy is called a stamp, or sometimes a service unit, Scale unit or cell. In a multi-tenant environment, every stamp or scale unit can serve as a predefined number of tenants. Multiple stamps can be deployed to scale the solution almost linearly and serve an increasing number of tenants. This approach can improve the stability of your solution, allowing you to deploy instances across multiple regions and separate your customer data. Consider grouping resources in scale units and provisioning multiple copies of your stamp. Each scale unit will host and serve a subset of your tenants. Stamps operate independently of each other and can be deployed and updated independently. A single geographic region might contain a single stamp or might contain multiple stamps to allow for horizontal scale out within the region. When implementing the deployment stamp pattern, several issues and considerations need to be addressed to ensure a successful deployment. It's crucial to have automated and fully repeatable deployment processes. Tools like Bison, ARM templates, or Terraform modules can be used to clearly define your stamps and keep the definitions consistent across stamp operations. When your solution is deployed across multiple stamps, operations that span multiple stamps, such as aggregating customer data, can become complex. Queries might need to be executed against each stamp and the results aggregated. Alternatively, consider having all stamps publish data into a central data warehousing for consolidated reporting. Determining the scale-out policies. So stamps have finite capacity, which might be defined using a proxy metric, such as a number of tenants that can be deployed into the stamp. It's important to monitor the availability and use capacity for each stamp and proactively deploy additional stamps to accommodate new tenants. It's advisable to deploy at least 2 stamps in your solution to avoid hard coding assumptions into your code or configuration that won't apply when you scale out. Deploying multiple copies of your infrastructure components will likely involve substantial increase in the cost of operating your solution. This includes the cost of additional memory, compute, and other resources required for each stamp. Moving between stamps. So each stamp is deployed and operated independently, so moving tenants between stamps can be difficult. Custom logic is needed to transmit customer information to a different stamp and remove it from the original stamp. The process might require a backplane for communication between stamps, further increasing the complexity of the solution. Routing traffic to a correct stamp for a given request can require an additional component to resolve tenants to stamps. This component needs to be highly available to ensure reliable traffic routing. Shared components. Some components might be shared across multiple stamps. For example, a shared single page app for all tenants could be deployed in one region and then replicated globally using Azure CDN. For multi-region applications, each tenant data and traffic should be directed to a specific region. This ensures that requests are routed to the correct stamp based on the user's geographic location. Stamps are independent of one another, so if one outage affects a single stamp, tenants deployed to other stamps should not be affected. This isolation helps to contain the blast radius of an incident or an outage, handling single and multi-tenant instances. So this pattern should support both single and multi-tenant instances, ensuring that each tenant's data is isolated and secure. Different stamps might need to be on different versions of your solution at a time. This requires careful management of updates and version control across your stamps. By considering these issues and implementing appropriate strategies, the deployment stamp pattern can effectively be used to improve the scalability, resiliency, and manageability of your solution. The deployment stamp pattern is useful in the following scenarios. Natural limits on scalability. If certain components of your system cannot or should not scale beyond a specific number of customers or requests, the deployment stamp pattern allows you to scale up by deploying multiple instances or stamps of your solution. Tenant isolation. When there's a requirement to separate certain tenants from others due to security concerns or compliant requirements, the deployment stamp pattern can be used to deploy those tenants into their own isolated stamps. For applications that need to be deployed across multiple regions, each tenant's data and traffic can be redirected to a specific region. This ensures the requests are routed to the correct stamp based on the user's geographic location. Stamps are independent of one another, so if an outage affects a single stamp, tenants deployed to other stamps should not be affected. This isolation helps to contain the blast radius of an incident or outage, enhancing the overall resiliency of their services, different versions of the solution. So if you need to have some tenants on different versions of your solution at the same time, the deployment stamp pattern allows a flexibility by deploying different stamps with different versions. High-scale platforms. This pattern is suitable for implementing high-scale platforms that have users distributed over a wide area. It helps on managing the load and ensuring that the system can handle a large number of users efficiently. By using the deployment stamps pattern in these scenarios, you can achieve better scalability, isolation, and resiliency for your application. So, deployment stamps is instrumental in managing large-scale deployments across multiple regions, availability zones, ensuring that your application remains robust and available to users worldwide. So let's install this concept and its practical implementation in Azure. So at the forefront of our architecture is the Azure Front Door service, which acts as a global entry point for our users. This service provides load balancing, traffic management, and high availability by directing user requests to the appropriate backend service based on various criteria, such as latency, geographic location, and availability. Within each region, a traffic controller manages the distribution of incoming requests across multiple deployment stamps. This controller ensures that the workload is evenly balanced and that no single stamp is overwhelmed with requests. By distributing traffic efficiently, we enhance the overall performance and reliability of our application. So this is using Traffic Manager as an example. So let's take a look a bit more into the deployment stamps as well. This core concept involves the use of multiple deployment stamps within a single region. Each stamp is a self-contained unit consisting, in this case, of Kubernetes services and various availability zones. This diagram illustrates three regions, each with multiple deployment stamps. Within each stamp, services are deployed across multiple availability zones, providing redundant and fault isolation. This setup ensures that if one zone or stamp experiences issues, the others can continue to operate without disruption. Each deployment stamp leverages Kubernetes services to orchestrate and manage containerized applications. Kubernetes provides robust capability for scaling, self-healing, and rolling updates, making an ideal choice for managing microservices at scale. By deploying services within a Kubernetes cluster, we can achieve a high degree of automation and resilience, allowing the systems to handle varying workloads dynamically. The combination of regional traffic controllers and multiple deployment stamps ensures that our application has both regional and global redundancy. This design allows us to provide uninterrupted service to users even in the face of regional outages or significant traffic spikes. In the event of a failure in one region, Azure Front Door can seamlessly route traffic to other regions, ensuring the users experience minimal disruption. In conclusion, the deployment stamps is a powerful approach to building scalable, resilient, and high available cloud applications by leveraging regional redundancy, traffic management, Kubernetes orchestration. We can deliver a seamless and reliable experience to users across the globe. So the bulkhead pattern is a type of application design that is tolerant to failures. In the bulkhead architecture, elements of the application are isolated into pools. So if one fails, the others will continue to function. It's named after the section partitions bulkheads of a ship's hull. If the hull of a ship is compromised, only the damaged section fills with water, which prevents a ship from sinking. A cloud-based application may include multiple services, with each service having one or more consumers. Excessive load or failure in a service will impact all consumers of that service. Partition service instances into different groups based on consumer load and availability requirements. This design helps to isolate failures and allow you to sustain service functionality for some consumers even during a failure. The bulkhead pattern and deployment stamp pattern are both architectural patterns used to improve the resiliency and scalability of applications, but they address different concerns and are implemented in different ways. For example, the deployment stamp pattern isolates entire instances of applications, each with its own services. The bulkhead pattern isolates different components or services within the same application or system and is primarily focused on fault isolation and resource management within a single deployment. These two patterns can work together for a highly resilient solution. So the bulkhead pattern is designed to improve the resiliency of an application by isolating different parts of the system to prevent a failure in one part from cascading to others. So let's take a look at some of the issues and considerations when we would look at implementing the bulkhead pattern. So for resource exhaustion, so if a service or consumer fails or becomes misconfigured, it can exhaust resources such as connection pool, memory, or CPU. This can prevent services or consumers from functioning properly. Cascading failures. So without isolation, a failure in one service can lead to cascading failures affecting the entire system. This can happen if a single service consumes all the available resources, leaving none for any other service. Implementing the bulkhead pattern does add complexity to the system. It requires careful planning and management of resource allocation and isolation. Isolating resources for different services or consumers can lead to less efficient use of resources. For example, some resources may remain underutilized while others are overutilized. Some considerations include partitioning services and consumers. So services and consumers should be petitioned based on different groups based on load and availability requirements. This helps to isolate failures and maintain service functionality for some consumers even during a failure. Allocate separate resources, i.e. connection pools or memory, for each service or consumer. This ensures that a failure in one service does not affect the resources available to other services. A consideration is the granularity of your bulkheads. Determine the appropriate level of granularity for bulkheads. For example, you could isolate resources at the service level, consumer level, or even at the tenant level. Consider combining the bulkhead pattern with other fault handling patterns such as retry, circuit breaker, and throttling to provide a more sophisticated fault handling. You need to evaluate the overhead in terms of cost, performance, and manageability when petitioning services or consumers into bulkheads. For example, using containers can offer a good balance of resource isolation with fairly low overhead. You need to monitor the performance and SLA of each petition to ensure that the isolation is effective and that the resources are used efficiently. Isolate critical consumers from standard consumers to ensure that critical operations can continue even if standard operations fail. The segmentation between components can help constrain security incidents to the compromised bulkhead, enhancing the overall security of the system. By addressing these issues and considerations, the bulkhead pattern can help improve the resiliency and reliability of your application, ensuring that the failures are contained and do not affect the entire system. So the bulkhead pattern is particularly useful in the following scenarios. Isolating resources for backend services. So use the bulkhead pattern to isolate resources used to consume a set of backend services. This is especially important if the application can provide some level of functionality even when one of the services is not responding. Implement the bulkhead pattern to isolate critical consumers from standard consumers. This ensures that critical operations can continue even if standard operations fail, protecting your application from cascading failures. So the bulkhead pattern helps protect your application from cascading failures by isolating different parts of the system. A failure in one part does not affect the entire system. Handling resource exhaustion. So when a service or a consumer fails or becomes misconfigured, it can exhaust resources such as the connection pools, memory, or CPU. The bulkhead pattern helps to prevent this by isolating resources for different services or consumers. The bulkhead pattern allows you to sustain service functionality for some consumers even during a failure. By partitioning service instances into different groups based on consumer load, availability requirements, you can isolate failures and maintain service functionality. Consider combining the bulkhead pattern with other fault handling patterns. The bulkhead pattern allows you to deploy services that offer different quality of service for consuming applications. For example, a high priority consumer pool can be used to configure high priority services. By using the bulkhead pattern in these scenarios, you can improve the resiliency and reliability of your application, ensuring that the failures are contained and do not affect the entire system. So the bulkhead pattern is inspired by the design of the ship compartments, where individual sections can be sealed off to prevent flooding from spreading throughout the vessel. Similarity with cloud architecture, the bulkhead pattern isolates components to prevent failures from cascading to the entire system. So let's dive into key elements and implementations of the bulkhead pattern. So our journey begins with the client applications that send requests to other services. These requests are first routed through an Azure load balancer, which distributes the traffic evenly across multiple instances of our application. This load balancing ensures that no single instance is overwhelmed with too many requests. At the heart of our architecture is Azure Kubernetes Service, or AKS. AKS provides a managed Kubernetes environment, allowing us to deploy, manage, and scale containerized applications seamlessly. With AKS, we can have multiple namespaces representing different services and components. This separation ensures that each service operates in its own isolated environment, akin to bulkheads on a ship. The front-end services handle incoming requests from the load balancer and route them back to the appropriate back-end services. The ingress controller then manages the routing, ensuring that the traffic is directed correctly based on predefined rules. The back-end services are further isolated into different namespaces, each responsible for specific functionalities. This isolation ensures that a failure in one back-end service does not impact the others, thereby enhancing the overall resilience of the system. In addition to core application services, we can have utility services such as Elasticsearch and Prometheus. These services provide essential functionality such as logging, monitoring, and alerting. By isolating utility services in their own namespace, we ensure that they operate independently of the main application components, further strengthening our bulkhead architecture. Our architecture also integrates with external data stores, including SQL Database and Azure Cosmos DB. These databases are critical for storing and retrieving application data. The integration with external data stores is managed in a way that ensures high availability and redundancy, preventing data access issues from affecting our application's performance. Continuous integration and continuous deployment (CI/CD) are facilitated through Azure pipelines. The CI/CD pipelines automate the process of building, testing, and deploying our applications, ensuring that our new updates are rolled out smoothly. Docker images are stored in Azure Container Registry, from where they are pulled into the AKS cluster. This setup allows for seamless deployment and scaling of containerized applications. Security and monitoring are critical aspects of our architecture. Enter ID provides role-based access control, ensuring that only authorized users can access and manage our applications. Azure Monitor and Azure Key Vault are used for monitoring application performance and securely managing secrets, respectively. These tools can help maintain the operational health and security of our system. In conclusion, the bulkhead pattern is a powerful approach to building resilient cloud architecture. By isolating components and services, we prevent failures from cascading and ensure that our application remains robust and reliable. This pattern, combined with Azure's powerful tools and services, allows us to deliver high quality, scalable, and secure applications to our users. So when you want to use an event, so when you use an eventually consistent operation that consists of a series of steps, the compensating transaction pattern can be useful, specifically if one or more of those steps fail. You can use the compensating transaction pattern to undo the work that the steps performed. Typically, you would find operations that follow the eventual consistency model in cloud hosted applications that implement complex business processes and workflows. Applications that run in the cloud frequently modify data. This data is sometimes spread across various data sources in different geographic locations. To avoid contention and improve performance in a distributed environment, an application shouldn't try to provide strong transactional consistency. Rather, the application should implement eventual consistency. In the eventual consistency model, a typical business operation consists of a series of separate steps. While the operation performs these steps, the overall view of the system state might be inconsistent, but when the operation finishes and all the steps run, the system should become consistent again. The data that is affected by an operation that implements eventual consistency isn't always held in a database. For example, consider a service-oriented architecture SOA environment. An SOA operation can invoke an action as a service and cause a change in the state that's held by that service. To undo the operation, you also have to undo the state change. This service can involve invoking the service again and performing another action that reverses the effect of the first. The solution is to implement a compensating transaction. The steps in a compensating transaction undo the effects of the steps in the original operation. And an intuitive approach is to replace the current state with the state of the system was in at the start of the operation. But a compensating transaction can't always take that approach because it might overwrite changes that other concurrent instances of an application have made. Instead, a compensating transaction must be an intelligent process that takes into account any work that any concurrent instances do. This process is usually application specific, driven by the nature of the work that the original operation performs. So when implementing the compensating transaction pattern, there are several issues and considerations that we need to keep in mind determining failure. So it might not be easy to determine when a step in an operation that implements eventual consistency fails. A step might not fail immediately, but could get blocked. Implementing a timeout mechanism can help identify such failures. Compensating logic is often application specific and relies on the application having sufficient information to undo the effects of each step in a failed operation. Generalizing this logic can be challenging. Defining the steps in a compensating transaction as idempotent commands. This ensures that the steps can be repeated if the compensating transaction itself fails, which is crucial for maintaining consistency. The infrastructure handling the steps must be resilient, both in the original operation and in the compensating transaction. It should not lose the information required to compensate for a failing step and must reliably monitor the progress of your compensation logic. A compensating transaction doesn't necessarily return the system data to the state at the start of the original operation. Instead, it compensates for the work that the operation completed successfully before it failed. In order for the steps in the compensating transaction isn't necessarily the exact opposite of the steps of the original operation. For example, one data store might be sensitive to the inconsistencies of another, so the steps that undo changes in this store should occur first. Concurrency and parallelism. It might be possible to perform some of the undo steps in parallel depending on how the compensation logic is designed for each step. This can speed up the compensation process. In some cases, manual intervention might be needed, might be the only way to recover from a step that's failed. The system should raise an alert and provide as much information as possible about the reason for the failure. To increase the likelihood of overall activity success, you can place a short-term timeout-based lock on each resource required to complete an operation. You can obtain these resources in advance and perform the work only after requiring all the resources, finalizing all actions before the locks expire. You can implement retry logic that is more forgiving than usual to minimize failures that trigger a compensating transaction. If a step in an operation fails, you can handle that as a failure and a transient exception and repeat the step. Stop the operation and initiate a compensating transaction only if a step fails repeatedly or can't be recovered. By considering these issues and implementing appropriate strategies, you can effectively manage the complexities associated with compensating transactions and ensure the reliability and consistency of your application. So the compensating transaction pattern should be used in the following scenarios: undergoing operations and eventual consistency models. So use this pattern to undo operations that implement the eventual consistency model. This is particularly useful if you need to maintain data consistency across distributed systems. Handling failures and long-running transactions. So when dealing with long-running transactions that involve multiple steps, the compensating transaction pattern can be used to undo the effects of each step if the transaction fails at any point. This ensures that the system can recover gracefully from failures, ensuring reliability and resilience. Implementing this pattern to address malfunctions and critical workload paths by rolling back data changes, breaking transaction locks, or executing native system behavior to reverse the effects. This helps in making the workload resilient to malfunctions and ensures it recovers to a fully functional state after failure. Complex business process and workflows. Use the compensating transaction pattern in cloud-hosted work applications that increment complex business processes and workflows. This pattern helps in managing eventual consistency and ensuring that the system can handle failures effectively, avoiding the complexity of distributed transactions. So whether it's feasible or not to use distributed transactions due to their complexity and overhead, the compensating transaction pattern can be an alternative. It allows you to break down the distributed transaction into several compensatable tasks. Handling state changes in the service-oriented architecture, so SOA. So in a service-oriented architecture environment where operations can cause changes in the state held by services, the compensating transaction pattern can be used to undo those state changes if necessary. By using the compensating transaction pattern in these scenarios, you can ensure that your system can handle failures gracefully, maintain data consistently, and recover from errors effectively. So in this example, customers use a travel website to book itineraries. A single itinerary might consist of a series of flights and hotels. A customer who travels from Seattle to London and then to Paris might perform the following steps when creating an itinerary. Book a flight from Seattle to London, book a seat from London to Paris, book a seat from Paris to Seattle, reserve a room at hotel in London, reserve a room at a hotel in Paris. These steps um, consist in eventually consistent operation. Although each step is a separate action, besides performing these steps, so the system must also record the counter operations for undoing each step. This information is needed in case a customer cancels the itinerary. The steps that are necessary to perform the counter operations can then run as a compensating transaction. In many business solutions, failure of a single step does not necessitate rolling back the system by using a compensating transaction. For example, consider the travel website scenario. Suppose the customer books flight F1, F2, and F3, but can't reserve a room at Hotel A. It's preferable to offer the customer a room at a different hotel in the same city rather than canceling the flights. The customer can then still decide to cancel. If that case, the compensating transaction runs and undoes the bookings for flights 1, 2, and 3, but the customer should not make this decision. But the customer should make this decision, not the system. So as we continually evolve in our digital age, ensuring robust security mechanisms is paramount. The four security patterns we will discuss today are backends for front ends, gatekeeper, federated identity, and gateway offboarding. So we're going to dive into backends for front-ends pattern. This design pattern advocates for creating separate backend services tailored to be consumed by specific front-end applications or interfaces. By adopting this pattern, we can significantly enhance the performance and security of our applications. Each front-end gets a backend that is optimized for its specific needs, reducing the attack surface, ensuring that only the necessary data is exposed. This separation also allows for more granular control of access and permissions, providing an additional layer of security. Next, we have the gatekeeper pattern. In terms of this approach, we approach our application and services by using a dedicated host instance that brokers requests between our clients and the applications and service. The gatekeeper acts as a security guard, ensuring that only authenticated and authorized requests are forwarded to the service. This pattern helps to shield our backend services from direct exposure to the internet, mitigating the risk of direct attacks. Additionally, it can enforce security policies and perform necessary checks, making sure that our systems remain secure and resilient against unauthorized access. Moving on, we have the federated identity pattern. This pattern involves delegated authentication to an extended external identity provider. By leveraging external identity providers, we can simplify the development process, minimizing the requirement for a user administration and improve the user experience of our application. Users can authenticate using their existing credentials from a trusted identity provider, reducing the need to manage multiple passwords. This not only enhances security by relying on well-established authentication mechanisms, but also provides a seamless logon experience using for users across multiple platforms and services. Lastly, we'll discuss gateway offloading pattern. This pattern involves offloading shared or specialized service functionality to a gateway proxy. Gateways can handle tasks such as authentication, rate limiting, logging, and SSL termination, thereby offloading these responsibility for individual services. We can centralize these functions to ensure a consistent we can ensure we have consistent security policies across all our services and reduce the complexity for each individual service. This approach also improves scalability and manageability, as changes to security policies can be made in one place and automatically apply to all services beyond the gateway. So the backend for front ends, or BFF pattern, involves creating separate backend services tailored to specific front-end applications or interfaces. This pattern is particularly useful if you want to avoid customizing a single backend for multiple interfaces, which can lead to conflicting requirements and development bottlenecks. An application may initially target a desktop web UI with a backend service developed to support it. As the user base grows, a mobile application might be developed that needs to interact with the same backend. However, the capabilities and requirements of mobile devices differ significantly from desktop browsers, leading to competing requirements for the backend. An application may initially targeted for the back. However, the capabilities and requirements differ. So yeah, you've got your different backend for your different front ends. When implementing the backend for front ends pattern, there are several issues and considerations that we need to keep in mind. Number one, competing requirements. So different front ends like desktop web UI, mobile applications have varying requirements in terms of screen size, performance, and display limitations. These differences can lead to competing requirements for the backend, making it challenging to serve both interfaces effectively. The backend can also become a bottleneck in the development process due to the need to accommodate conflicting update requirements from different front-end teams. This can result in significant effort being spent on maintaining a single deployable resource that serves multiple front ends. Maintaining separate backends for each front end can increase the complexity of the system. Each backend needs to be updated and maintained independently, which can lead to an increased operational overhead. The backend for front-end pattern introduced segmentation and isolation by creating separate backend services for each front-end. This reduces the surface area of the API and limits lateral movement among different backends, which might expose different capabilities. This separation allows for tailored security and authorization mechanisms for each front end. This ensures that the security requirements for each front end are addressed effectively, potentially reducing the surface area of an API. By creating separate backends for each client, you can expose an optimal interface for this client. This allows for different payload sizes or interaction patterns that are specific to the needs of each frontend, improving performance and user experience. The BFF pattern reduces the attack surface by limiting the functionality exposed by each backend to only what is necessary for its corresponding frontend. This minimizes the potential for security vulnerabilities. The separation of backends allow for more granular monitoring and control over each service. Security incidents can be constrained within the specific backend, reducing the blast radius of any potential compromise. Different frontends may have different compliance and regulatory requirements. The BFF pattern allows for these requirements to be addressed individually, ensuring that each backend complies with the necessary standards. By considering these issues and implementing appropriate strategies, you can effectively manage the complexity associated with the backend for frontends pattern and ensures that reliability, security, and performance of your application. The backends for frontends or BFF pattern should be used in the following scenarios: different client requirements. So when different types of clients, such as your mobile applications and your desktop web browsers, require different payload sizes or interaction patterns, the BFF pattern is useful. It allows you to create separate backends for each client, which exposes an optimal interface for that client. If the backend service becomes a bottleneck due to conflicting update requirements from different front-end teams, the BFF pattern can help by creating a separate backend service for each front-end. You can reduce the effort spent on maintaining a single deployable resource that serves multiple front-ends. When the capabilities of different front-ends differ significantly, leading to competing requirements for the backend, the backends for front-end pattern can address those differences. It allows for each backend to be optimized for the specific needs of the corresponding front-end. All right, let's take a look at. So the backend for front-end pattern is essential for optimizing the interaction between front-end applications and backend services, ensuring efficient communication, scalability, and maintainability. Let's explore the architecture and implementation of backends or frontends as depicted in this diagram. So at the entry point of our architecture, we have the application gateway. This component acts as a reverse proxy handling incoming HTTP requests, providing load balancing, SSL termination, and web application firewall capabilities. The application gateway ensures that user requests are efficiently routed to the appropriate front-end services, enhancing security and performance. The front-end services are responsible for handling user interactions and rendering the user interface. These services receive requests coming from the application gateway and process them accordingly. In this diagram, we can see that the front-end services depicted a layer that interacts directly with that application gateway. These services are designed to provide a responsive and dynamic user experience. The integration subnet serves as an intermediary layer that connects the front-end services to the back-end services. This subnet is essential for managing communication and data flow between the two layers. By isolating the integration subnet, we enhance our security and control over the traffic between the front end and the back end, ensuring that only authorized communication takes place. The backend services are hosted within a dedicated backend subnet. These services are responsible for the core business logic, data processing, and integration with databases and other external systems. We can see that the backend service is connected to the front end through the integration subnet. This separation ensures that the backend services are shielded from direct exposure to the internet, enhancing security and scalability. By adopting the backends for front-end pattern, we achieve a highly scalable and maintainable architecture. Each layer can be scaled independently based on demand, ensuring optimal performance and resource utilization. This pattern also enhances maintainability by allowing developers to work on front-end and back-end services independently, reducing complexity and improving development efficiency. In conclusion, the backend for frontends pattern is a powerful approach to structuring modern cloud applications by clearly separating front-end and back-end services and managing their interaction through dedicated subnets. We achieve a secure, scalable, and maintainable architecture. This pattern ensures that our applications can handle increasing loads while also providing a seamless and responsive user experience. So cloud services expose endpoints that allow client applications to call their APIs. The code is then used to implement the API triggers and perform several tasks, including but not limiting to authentication, authorization, parameter validation, and some or all request processing. The API code is likely to access storage and other services on behalf of the client. If a malicious user compromises the system and gains access to the application hosting environment, its security mechanism access to data and other services are exposed. As a result, the malicious user can gain unrestricted access to credentials, storage keys, sensitive information, and other services. The gatekeeper pattern allows you to protect applications and services by using a dedicated host instance to broker requests between clients and their application or services. The broker validates and sanitizes the request and can provide an additional layer of security and limit the system's attack surface. The gatekeeper pattern is a design pattern used to protect applications and services by acting as an intermediary that validates and sanitizes requests before passing them to the trusted host. Here are some of the key issues and considerations when implementing this pattern. Single point of failure. So the gatekeeper instance could become a single point of failure. If the gatekeeper fails, it can disrupt the entire system. To mitigate this, consider deploying redundant instances and using an auto-scaling mechanism to ensure capacity and maintain availability. Adding the gatekeeper layer introduces additional processing and network communication, which can impact the overall performance of the system. This additional latency needs to be considered, especially for performance-critical applications. Implementing the gatekeeper pattern adds complexity to the system architecture. It requires careful design to ensure that the gatekeeper effectively validates and sanitizes requests without becoming a bottleneck for or introducing new vulnerabilities. control validation. So the gatekeeper should validate all incoming requests and yeah, reject those that do not meet the validation requirements. This helps in ensuring that only legitimate requests are processed by the trusted host. The gatekeeper should also not have access to the credentials or keys used by the trusted host to access the storage and services. This limits the risk and exposure in case the gatekeeper itself is compromised, as the attacker would not gain access to these sensitive credentials or keys. The gatekeeper should run in a limited privilege mode while the rest of the applications run in full trust mode required to access storage and services that it needs. This ensures that even if the gatekeeper is compromised, it cannot directly access the applications or data or services. Secure communication. So use secure communication channels, HTTPS, SSL, TLS, between the gatekeeper and the trusted hosts or tasks. This helps in protecting the data in transit and ensures that the communication between the gatekeeper and the trusted host is secure. Ensure that the trusted hosts expose only the internal or protected endpoints that are used exclusively by the gatekeeper. The trusted host should not be exposed The trusted host should not expose any external endpoints or interfaces to minimize the attack surface. To minimize the impact of a failure, make sure you do deploy redundant instances of the gatekeeper and use auto-scaling mechanisms to ensure that there's always sufficient capacity to handle incoming requests. The gatekeeper should not perform any processing related to the application or services or access any data. Its function should be purely to validate and standardize requests. The trusted host might need to perform additional request validation, but the core validation should be done by the gatekeeper. By considering these requests and implementing appropriate strategies, you can effectively manage the complexities associated with the gatekeeper pattern and ensure reliability, security, and performance of your application. The gatekeeper pattern should be used in the following scenarios: handling sensitive information. When your application handles sensitive information that requires a high degree of protection from malicious attacks, the gatekeeper pattern is beneficial, as it acts as an intermediary that validates and sanitizes requests before they reach the trusted host, thereby protecting that sensitive data. If your application exposes services that require robust security measures such as web application firewalls, DDoS protection, bot detection, and centralized authentication authorization checks, the gatekeeper pattern can centralize these security functionalities. For applications that perform mission-critical operations that cannot be disrupted, the gatekeeper pattern ensures that only validated and sanitized requests are processed, reducing the risk of malicious attacks and system failures. When there's a need to perform request validation separately from the main task or to centralize this validation to simplify maintenance and administration, the gatekeeper pattern is appropriate. It ensures that the core validation is done by the gatekeeper, while the trusted host might also just perform additional validation, reducing the attack surface. So the gatekeeper pattern is useful when you want to reduce the attack surface of your system by decoupling the public endpoints from the code that processes requests and access storage. The gatekeeper can provide an additional layer of security and limit the system's exposure to potential attacks. When secure communication between clients and their application or service is required, the gatekeeper pattern can be implemented using secure communication channels, HTTPS, TLS, SSL, TLS, between the gatekeeper and the trusted hosts or tasks. In scenario where high availability is crucial, deploying redundant instances of the gatekeeper and using an auto scaling mechanism can ensure that there's always sufficient capacity to handle incoming requests, minimizing the impact of failure. By using the gatekeeper pattern in these scenarios, you can enhance the security, reliability, and performance of your application, ensuring that it meets the necessary protection and operational requirements. In an era where cyber threats are increasingly sophisticated, it is critical to fortify our applications against potential vulnerabilities and attacks. The Gatekeeper pattern provides a robust solution for this, ensuring that our applications are secure and resilient. Let's dive into the key components and implementation of the Gatekeeper pattern, as we can see in this diagram. So this diagram highlights the various security threats that our applications may face, including the OOPS top 10 vulnerabilities, SQL injection, cross, cross-site scripting, session hijacks, and denial of service attacks. These threats can have severe consequences comprising the integrity, confidentiality, and availability of our application. Therefore, it's imperative to implement robust security measures to mitigate these attacks. At the forefront of our security architecture is the application gateway, integrated with a web application firewall or WAF. This application gateway serves as a first line of defense, filtering and inspecting incoming traffic before it reaches our web applications. The WAF is a critical component that provides protection against common web vulnerabilities by analyzing HTTP requests and applying security rules. It effectively blocks malicious traffic, ensuring that only legitimate requests are forwarded to the backend services. Our architecture is hosted within a virtual network, which provides an isolated and secure environment for our applications. This VNet ensures that communication between different components is secure and controlled. By isolating our application environment, we reduce the attack surface and enhance the overall security posture of our architecture. The core of our application resides within the web app, hosted in a web app service environment. This environment provides a fully managed platform for running web applications, offering high availability, scalability, and security. The app service ensures that our web applications are isolated from other tenants by providing an additional layer of security and control. Our architecture seamlessly integrates with various other Azure services, including API management, Azure Storage, SQL Database, and Azure Cosmos DB. These services provide essential functionalities for data storage, management, and retrieval. The integration is managed through secure connections within the VNet, ensuring that data flows securely between the different components of the architecture. Implementing the gateway pattern involves adhering to security best practices such as regular updates, patching, monitoring, logging, and employing strong authentication and authorization mechanisms. Continuous monitoring and analysis of security logs helps in detecting and responding to potential threats in real time, further enhancing the security of our applications. In conclusion, the Gatekeeper pattern is a powerful and essential approach to securing web applications. By leveraging an Azure application gateway with WAF, isolated VNets, and a managed app service environment, we can ensure that our applications are protected against a wide range of cyber threats. This pattern not only fortifies our defenses, but also provides scalable and resilient architecture for delivering secure web services. So delegating authentication to an external identity provider can simplify development, minimize the requirement for a user administration, and improve the user experience of the application. This is where federated identity pattern comes into play. Users typically need to work with multiple applications provided and hosted by different organizations that they have a business relationship with. You can implement an authentication mechanism that can use federated identity, separate users' authentication from the application code, and delegate authentication to a trusted identity provider. So I'm just having a drink. This model is often called claims-based access control. Applications and services authorize access to features and functionality based on the claims contained in the token. The service that requires authentication must trust the IDP, so identity provider. The client application contacts the IDP that performs the authentication. Federated authentication provides a standard-based solution to the issue of trusting identities across diverse domains. This type of authentication is becoming more common across all types of applications, especially cloud-hosted applications, because it supports single sign-on without requiring a direct network connection to identity providers. The user doesn't have to enter credentials for every application. This increases security because it prevents the creation of credentials required to access many different applications, and also hides the user credentials from all but from the original identity provider. Applications see just the authenticated identity information that's contained within the token. So when implementing the federated identity pattern, there are several issues and considerations to keep in mind. Single point of failure. Authentication can become a single point of failure if the identity provider or IDP or the security token service or STS fails. It can disrupt access to all applications relying on it. To mitigate this, consider deploying your identity management mechanism across multiple data centers to maintain reliability and availability. Implementing federated identity can be complex, especially if retrofitting it into an existing application that were built using different authentication mechanisms. This complexity can make it less cost effective and more challenging to manage. The additional steps involved in federated credentials, such as token issuance and validation, can introduce latency. This performance impact needs to be considered, especially for applications requiring high responsiveness. Federated identity can expose security vulnerabilities if not properly managed. For example, if a user leaves the company and their account is not immediately deprovisioned, it can lead to unauthorized access. Ensuring timely deprovisioning and robust security practices is crucial. While federated identity can reduce the administrative overhead of managing user credentials within the application, it requires careful management of the relationship with the identity provider. This include this includes ensuring that the identity provider's security practices are robust and that integration is maintained. Role-based access control. So federated identity allows the implementation of role-based access to control, or RBAC, based on role claims contained within the authentication token. This provides a more granular level of control over access to features and resources within the application. If there are multiple identity providers configured, the STS must determine which identity provider the user should be redirected to for authentication. This process, known as home realm discovery, can be automated based on various factors such as email address, subdomain, IP address, or cookies. Federated identity can improve the user experience by enabling single sign-on or SSO across multiple applications. Users do not need to remember multiple credentials, which simplifies their interaction with the system and reduces the likelihood of forgotten passwords. Offloading user management and authentication to a trusted identity provider can enhance security by leveraging the provider's advanced capabilities for identity-based threat detection and prevention. This also helps in meeting compliance requirements without implementing these capabilities in the application itself. Federated systems typically require a load-balanced array of servers to ensure high availability for authentication requests. This setup helps in maintaining business continuity by providing redundancy and failover capabilities. Federated identity is useful for integrating with third-party services and applications, especially in scenarios where multiple organizations need to collaborate to allow users from different organizations to authenticate using their own credentials, simplifying access management. By considering these issues and implementing appropriate strategies, you can effectively manage the complexities associated with the federated identity pattern and ensure the reliability, security, and performance of your application. The federated identity pattern should be used in the following scenarios. Single sign-on for the enterprise. So this is our most common one. When you need to authenticate employees for corporate applications hosted in the cloud outside of the corporate security boundary without requiring them to sign in every time they visit an application. This provides a seamless user experience similar to on-premises applications where users authenticate once and gain access to all relevant applications. Federated identity with multiple partners. So when you need to authenticate both corporate employees and business partners who do not have accounts in the corporate directory, this is common in business to business applications that integrate with third-party services and scenarios where companies with different IT systems have merged or shared resources. SaaS applications. For independent software vendors providing a ready-to-use service for multiple clients or tenants. Each tenant can authenticate using a suitable identity provider, such as corporate credentials for business users or social identity credentials for consumers and clients of the tenant, improving user experience. So when users typically need to work with multiple applications provided and hosted in different organizations, federated identity can simplify the user experience by allowing them to use the same credential across all applications. This reduces the likelihood of forgotten passwords and provides a more cohesive user experience. When you want to minimize the administrative overhead of managing user credentials within the application by delegating authentication to a trusted identity provider, you can simplify development and reduce the need for user administration tasks such as password reminders and account deprovisioning. Enhance security. So when you want to enhance security by offloading user management and authentication to a trusted identity provider, this can provide additional capabilities for identity-based threat detection and prevention and ensure that your user credentials are managed securely, supporting claims-based control. When you need to implement role-based access control, or RBAC, based on role claims contained within an authentication token, this allows for a more granular level of control over access to features and resources within the application. So, a federated identity solution, which is designed to streamline and secure user access across multiple systems and platforms. On the screen, you can see a visual representation of our federated identity architecture, which highlights integration between Entra ID and AWS IAM Identity Center. So let's break down the key components and flow of this architecture. So the Enter ID source tenant. So this serves as the initial point of user identity information. In our environment, we have multiple Enter ID source tenants, which house the primary user's identities. To ensure consistency and accuracy across different systems, we have implemented cross-tenant synchronization. This mechanism ensures that any changes or updates made on the source tenant are automatically reflected in the target tenant. This process, as depicted in the diagram, allows the tenant information to be shared into the shared identity target tenant. So the synchronized identity information from various source tenant is then consolidated into the Enter ID shared identity target tenant. This central repository of user identities is crucial for maintaining access and maintaining security. Finally, the consolidated identity information is integrated into the AWS IAM Identity Center. This integration allows users to access AWS resources seamlessly using their federated Entra ID credentials. This arrow from the Entra ID shared identity tenant to the AWS IAM Identity Center illustrates the target linkage. By implementing this federated identity solution, we have achieved the following benefits. Enhanced security by centralizing our identity management, which we've reduced the risk of unauthorized access and ensures that security policies are consistently enforced. Simplified user experience operational efficiency by automated synchronization between tenants, minimizing the administrative overhead associated with managing user credentials across different systems. In conclusion, our federated identity solution not only strengthens our security posture, but also enhances the overall user experience by providing seamless and secure access to essential resources. So, offload shared or specialized service functionality to a gateway proxy. This pattern, gateway offloading, this pattern simplifies application development by moving shared service functionality, such as the use of SSL certificates, from parts of the application onto the gateway. So offload some features onto the gateway, particularly cross-cutting concerns such as certificate management authentication, SSL termination, monitoring, protocol translation, or throttling. It is similar to the gateway pattern, which focuses primarily on protecting applications by validating and sanitizing requests, decoupling public endpoints from backend services, and centralizing security functionalities to limit the system's attack surfaces. The gateway offloading pattern focuses on offloading cross-cutting concerns and shared functionality to a gateway to simplify application development and maintenance and to enhance the security, consistency in logging and monitoring. When implementing the gateway offloading pattern, there are several issues and considerations to keep in mind. Coupling across services. So introducing a gateway can create coupling across services which might not be suitable for all architectures. This coupling can lead to dependencies that complicate the deployment and scaling of an individual service. The gateway itself can also become a single point of failure if not properly managed. It is crucial to ensure that the gateway is highly available and resilient to failures by running multiple instances and designing for capacity and scaling requirements of the application. Offloading functionality to a gateway can introduce performance overhead. The gateway must be designed to handle additional load without becoming the bottleneck for the application. This includes ensuring that the gateway can scale appropriately to meet the demands of the application. Properly handling security issues such as token validation, encryption, and SSL certificate management requires specialized skills. The gateway must be configured and managed by a team with the necessary expertise to ensure that security is not compromised. While offloading shared functionalities to a gateway can reduce administrative overhead in some areas, it can also introduce new administrative tasks. For example, managing and updating SSL certificates or other shared resources at the gateway level requires careful planning, coordination, and planning. The gateway can provide consistency in requests and response logging and monitoring. However, it's essential to ensure that the gateway is correctly instrumented to provide the necessary level of monitoring, logging, even if the individual services are not. Offloading specialized features such as authentication, authorization, logging, monitoring, or throttling to the gateway allows dedicated teams to manage these features. This can simplify the development and maintenance of the core application, but requires coordination between teams to ensure that the offloaded features are correctly implemented and maintained. Business logic should never be offloaded to the gateway. The gateway should only handle cross-cutting concerns that are used by the entire application, such as security or data transfer. Offloading business logic can lead to highly coupled architecture, which is difficult to maintain and scale. By considering these issues and carefully planning your implementation, you can effectively use the gateway offloading pattern to simplify application development, enhance security, and ensure consistency in logging and monitoring. The gateway offloading pattern should be used in the following scenarios: shared or specialized service functionality. So when you need to offload shared or specialized service functionality such as SSL certificate management, authorization, authentication, logging, monitoring, or throttling to a gateway proxy, This can simplify application development by moving these cross-cutting concerns from other parts of the application to the gateway, reducing administrative overhead. So when managing shared features across multiple services increases administrative overhead and the likelihood of deployment errors. Offloading these features to a gateway can reduce the need to configure, manage, and maintain them across all services, simplifying updates and reducing the risk of errors. When you need to handle complex security tasks such as token validation, encryption, and SSL certificate management, offloading these tasks to a gateway allows dedicated teams with specialized skills to manage them, ensuring security is not compromised. So I'm just having a drink. Consistency and logging and monitoring. When you want to ensure consistency in request and response logging and monitoring across services, the gateway can be configured to provide a minimum level of monitoring and logging even if individual services are not correctly instrumented. High availability and resilience. When you need to ensure that the gateway is highly available and resilient to failure, running multiple instances of the gateway and designing it for the capacity and scaling requirements of the application can help avoid single points of failure and ensure that the gateway does not become a bottleneck. When you want to simplify the configuration and management of supporting resources such as web service certificates and secure website configurations, offloading the responsibility to a gateway can make service upgrades simpler and more manageable. When you want to mitigate attacks at the edge and ensure that internet traffic routes only through the gateway, not directly to the workloads or PaaS platform as a service resources, the gateway should have the ability to mitigate exploits and provide network security. By considering these scenarios, we can determine whether the gateway offloading pattern is suitable for your application and ensures that it meets the necessary security, user experience, and administrative requirements. So the diagram on the screen showcases the architecture of our gateway offloading strategy, highlighting the role of the application gateway in our infrastructure. So let's delve into the key components and their functions. So the user initiates requests by accessing our domain contoso.com. These requests are then directed towards our application gateway. At the heart of our architecture, we have our application gateway. This component is responsible for efficiently managing and routing incoming traffic. It features Web Application Firewall, or WAF. This layer provides robust security by protecting our applications from common web exploits and vulnerabilities. Layer 7 Load Balancer. This functionality enables intelligent traffic distribution based on the application layer information, ensuring optimal resource utilization and performance. The application gateway also deploys content-based routing to direct requests to the appropriate backend server pools. A request for images designated by images /images are routed to the image server pool, which is optimized for serving image content. Requests for video are routed to the video server pool, which is optimized for video content delivery. The backend server pools, which consisting of the image server pool and video server pool, are specialized clusters designed to handle specific types of content. This specialization ensures that each type of content is delivered efficiently and effectively by our users. The Web Application Gateway Firewall layer, cat's trying to get out. The Web Application Firewall layer protects our applications from malicious attacks and unauthorized access, ensuring data integrity and confidentiality. The Layer 7 load balancing and content-based routing optimizes traffic distribution, reducing latency and improving the overall user experience. This architecture allows us to scale our backend server pools independently, accommodating increasing traffic demands without compromising performance. In conclusion, our gateway offloading solution is a pivotal component of our infrastructure, providing robust security, enhanced performance, and scalable resources to meet the dynamic needs of our users. So we've gone through quite a lot of patterns today in terms of from data management, security to design and implementation. Let's take a look at some of the resources to learn more about and read. So we've got our three fundamental pillars here. So we've got the Cloud Adoption Framework, the Azure Architecture Center, and the Well Architected Framework. So our first pillar, which is the Cloud Adoption Framework, provides proven guidance and best practices to help us seamlessly transition to the cloud. This comprehensive framework is designed to ensure that your adoption of the cloud is efficient, effective, and aligned with your business objectives. By following the framework, you can achieve tangible business outcomes and drive innovation. Next, we have the Azure Architecture Center. This serves as a beacon for designing robust and scalable solutions on Azure. This center offers invaluable guidance on established patterns and practices, ensuring that your architecture not only technically sound, but also optimized for performance and cost efficiency. By leveraging the resources available at the Azure Architecture Center, you can build solutions that are resilient, secure, and future-proof. Finally, we come to the well-architected framework. This framework is a set of quality-driven tenets, architectural decision points, and review tools designed to help solution architects build a strong technical foundation for their workloads. By adhering to these principles, you can ensure that your solutions are built to withstand the demands of today and the challenges of tomorrow. The well-architected framework provides a holistic approach to creating resilient, efficient, and scalable architectures. So, in conclusion, by embracing these three pillars, the Cloud Adoption Framework, the Azure Architecture Center, and the well architected framework, you're equipping your organization with the tools and knowledge necessary to excel in the cloud. So, we're just going to recap the core principles that drive effective design and implementation in the cloud, specifically with the Azure ecosystem. So, the design patterns are the building blocks of robust architecture. Understanding the categories and implementation options is crucial for any cloud strategy. So design patterns. At the heart of our discussions are design patterns. These are the tried and true solutions to common architectural challenges. Think of them as the building blocks, much like the colorful blocks depicted in our visual aid, that can be combined in various ways to create a resilient and scalable architecture. Design patterns provide a blueprint that helps streamline the development processes while ensuring consistency and reliability. Next, we'll dive into pattern categories. Each design pattern falls into a specific category based on the functionality and application. These categories help us understand the purpose and best use cases for each pattern. Whether you are dealing with data management, security, performance optimization, knowing the right category helps in selecting the most appropriate design pattern for your needs. Architecture. So architecture is where these design patterns come to life. By leveraging these patterns, we can construct architectures that are not only robust, but also flexible and scalable. The architecture we build should align with our business goals and technical requirements, ensuring that our solutions are both effective and efficient. Lastly, we'll focus on implementation options for Azure. Azure provides a plethora of services and tools to facilitate the implementation of these design patterns. Understanding how to utilize these options effectively allows us to deploy solutions that are optimized for the cloud, whether it's using Azure's native services or integrating third party tools. The goal is to create a seamless and efficient implementation that maximizes the benefits of the cloud. Mastering modern design patterns and their applications within Azure is key to building successful cloud solutions. By understanding design patterns, their categories, architectural implications, and implementation options, we equipped ourselves with knowledge to innovate and excel in the cloud. And the words of Satya Nadella resonate deeply when he says, the impact of technology on every part of our daily lives is greater than it's ever been. Indeed, we live in an era where technology is woven into the very fabric of our existence. From the moment we wake up to the sound of an alarm on our smartphones, to the way that we communicate, work, and even relax. Technology is our constant companion. It has transformed industries, reshaped economies, and connected us in ways that were once the stuff of science fiction. Yet, as we marvel at these advancements, we also must pause and reflect on the kind of technology that we're creating and embracing. Nadella's words guide us here too. What the world needs is technology that is trusted and benefits people and society as a whole. Trust. This is the cornerstone of our digital future. In an age where data breaches and cybersecurity threats loom large, the technology we build and use must be secure, transparent, and respectful of our privacy. We must foster an environment where people feel confident that their personal information is safe and their digital interactions are protected. But trust alone is not enough. Our technological advancements must also bring tangible benefits to society. They should bridge gaps rather than widen them, create opportunities instead of eliminating them, foster inclusivity instead of division, whether it's through providing accessible education, improving healthcare, or addressing climate change. Technology must be a force for good. As we stand at this crossroads, it is our collective responsibility to steer the course of technical development. Innovators, policymakers, educations, and every part of our end users must work together to ensure that technology serves humanity's best interests. Let us harness the power of technology to enrich our lives, empower our communities, build a future where everyone can thrive. Let us, let us commit to creating technology that not only is advanced but also ethical and humane. Thank you very much.